get started right away. So shoot, please.
Okay. Thank you everyone for coming to our workshop, AutoExpert, meaning auto annotation from an expert correctly the guidelines. First of all, I hope everyone wait, it doesn't work. Yeah, I hope everyone is safe and healthy. The goals for the workshop is to connect people and exchange ideas related to the topic auto expert and discuss new opportunities and challenges about this topic. This is a hybrid workshop. We have online fellows. Yeah, please enjoy and interact with each other. And we also have a virtual audiences in Zoom. The Zoom will be recorded and will be released after the conference. Okay, I want to introduce the topic auto expert by reminding people about the data annotation, which is the first class citizen in modern computer vision machine learning based solutions. Typically, for a specific application, we have a domain expert who will collect data and design annotation guidelines. And here is a snapshot of a new sense dataset, which is designed for autonomous driving. And autonomous driving experts designed the instruction to instruct ordinary human annotators how to annotate the unlabeled data, like the bicycle, the truck, right? There are a few visual examples for each class, and there are descriptions for the classes, right? And we have companies providing data labeling services like a Scale AI. We all know that, and we also have the CEO of, and a co-founder, Jason Corso from Voxel 51, which is a company doing data analysis and model evaluation here. So you see the standard pipeline to do annotation is to let the experts design the instructions and collect data and send it to human annotators to train them to follow the instructions to annotate data. We want to annotate a massive data to train expert model, right? The expert model here is for autonomous driving. If we don't train expert model, but just go with modern AI, then we have issues. Here's an illustration. I use a AI agent or the foundational detector called a grounding dyno to detect a truck and a bicycle, and that outputs green bounding boxes. You see, we cannot say the green bounding boxes are wrong because they capture the truck, the bicycle, but the issue is that the outputs do not align with expert level annotations. Why so? Because AI can understand the common knowledge. Oh, this is a bicycle, this is a truck, but experts take care of safety issues to annotate the rider within the bicycle and the truck head and the trailer separately because of different motions of the objects. That's why we need to train models, expert models, but the prerequisite is to annotate massive data. And actually, in many other disciplines, like applied behavior analysis, we do have professionals and experts annotate or code long videos to understand the behaviors like that. And actually, in ecology, we also have experts annotate data. Of course, they collect data and annotate data by themselves. And you see in also, on a zoology as well, we have a track camera, and the camera take long videos, and we need some experts to annotate or code or recognize the bird species to understand the biodiversity, environmental science, so on and so forth. And the whole procedure here, regardless of hiring human annotators, annotated data, or letting experts annotate the data by themselves, the whole procedure is labor intensive, tedious, and costly. And the annotations are erroneous, subjective, biased, and inconsistent among different individuals. That's why we want to study, oh, can we develop methods to automatically annotate the domain data with the domain expert crafted the annotation guidelines. And this is the motivation. And our philosophy here in the modern days is to embrace open resources, including open world data, open source models, foundation models, and we target realistic, challenging, and real world problems. To simulate the study, we have two challenges. One is for species level annotation based on annotation guidelines, and the other is for autonomous driving, following the instructions to annotate the 3D cuboids on LiDAR and RGB data. And this is the program schedule. Just enjoy all the talks. And here we have one wonderful speakers. We have so many people make it happen for the workshop. And I thank you, thank all of you here. Tian, please take over and introduce our first speaker.
Thank you, Shu. Thank you. Now it's my pleasure to introduce Professor James Hayes. James is a professor at the Georgia Institute of Technology and a pioneer in dataset construction. He has contributed to the community with many foundational datasets such as Sun, Cocoa, and Argoverse. Please join me in welcoming James and learning about his research. Thanks.
Hey, everybody, give me 1 second to set up here. And you want me to join the Zoom call?
Yeah. So they can.
All right, well, give me 1 second to do that as well. No. Like, oh, PowerPoint just disappeared there. Crashed silently. That's a great omen. Oh, I guess it was a forced update.
Oh, I hate Microsoft.
I can go ahead and get my screen shared here.
Yes, we can see your screen.
I'm just closing this. Okay. Hey, everybody, I'm James.
Would you mind turning on your Mac, please?
Turning what?
Your voice. Is it on?
Oh, I see. Unmuting on Zoom.
Yeah. Yeah.
Got it. It's my pleasure to speak with you. Please feel free to interrupt. It's not such a large group here anyway. And wait, what just happened to PowerPoint? I'm mostly going to be talking about one work, which I'll introduce in a second. But workshop has a lot of interesting topics, and I'm not going to be addressing a lot of these. The talk will touch on experts and how their annotations relate to VLN, I guess. So I am going to talk about data set benchmark construction and experts. In some sense, though, I'm going to be saying that this is a case where the experts are too good, but you prove me wrong, and we'll see. I do have some work that's related to one of the challenges that was just introduced. This idea of can we rebuild new scenes automatically? Like just give VLM or something the annotation instructions of new scenes, give it the 3D point clouds, and have it annotate it from scratch. Very cool idea. And my group has some work trying to take 2D foundation models and lift them to 3D. Here's an old one all the way from 2020. We didn't have the term foundation model back then. It was just center mask or something like this. But this idea that there's good models in 2D, there are no good models in 3D. So let's look at the images and somehow inflate the detections. It's an idea that's been pursued a lot of times. Part of the novelty here was that we had HD maps, which was new in 2020. And that helps you do this inflation. It helps you realize that, well, maybe I'm seeing a car here and it must be oriented this way because it's probably following the lane geometry. And then more recently, we have something very similar. Really, the difference is that now the foundation model is something better. You know, this is from only a year or two ago, but it's still the same idea. We're going to look at images in 2D and inflate them and wrap the LiDAR point clouds and get our 3D annotations for free. Except I don't call them annotations here. We call them pseudo labels because they're not really as trustworthy. Annotation is something lofty to me, right? Like a human expert put an annotation down and we can trust it. If it's something that's just derived from, it's the output of another AI model, then it's more like a pseudo label, I feel like. So yeah, I'm not sure that I would use the term auto annotation, although I was looking at a recent paper submission of mine based on this workshop invitation, and I saw that the title included the term auto labeling. Anyway, I think that means that the workshop is perfectly situated in time because these AI models are getting so good now, right? And even though I'm hesitant to say that if it came out of ChatGPT, then you probably shouldn't call it an annotation. But, you know, Gemini might be better than the average human annotator at this point. Probably average is probably true. So maybe the lofty term of annotation is justified. And even if Gemini is not as good as the average human annotator, there's probably a lot of tasks where the weak supervision that you get by just asking Gemini with its trillion or so parameters to auto-label your data, maybe that's still valuable. I can totally buy that. But I do think there's domains where the experts are still quite a bit better than the VLMs or whatever other models you're using. Maybe medical imaging, it's not my expertise. It's gotten a lot of attention, you know, radiologists and how they should collaborate with AI tools. I mentioned species identification because I think it's interesting. And again, that's the other workshop competition, right? So I guess I'm plugging that as well. And it is the expertise of some of the workshop organizers, not my expertise. But I'm skeptical that ChatGPT or Gemini could do as good a job at fine-grained recognition as the experts. What I am about to drill down in is geolocation, which is my expertise. And so that's the problem with just saying where a photo was taken. Pretty fundamental attribute of a photo that you would want to know. And it's actually, I think, a problem where you would expect the AI models would actually do great, and they do well, but you would think they would do better they'd be superhuman, right? Because knowing where a photo is taken is really a function of just looking at a lot of images of the world, and the AI models have done more of that than any human, right? So actually, it's sort of surprising, and maybe this is contrary to other published results. I think the experts are still better than the machines at this task, which is a bit surprising. But yeah, that I'm going to drill into for the rest of this talk. Again, feel free to interrupt me. Hopefully, it touches on some interesting points about experts and annotations and the state of AI with respect to experts. And this work is appearing in just a week or two at ACL. All right, this is going to be very interactive. I'm going to be asking you a lot of questions. First off, where is this photo taken? Everest. I've gotten that answer before. It's not Everest. And critically, it wasn't claimed to be Everest either. But I think this might have been the world's history's first geolocation challenge. Any other guesses? It's on this continent, but it's not in the state. Denali, great. So if you think that this is the top of Denali, then you are the friend of Frederick Cook, even though he's long dead, who was a dubious explorer who claimed to be the first person to summit Denali. He also claimed to be the first person to visit the North Pole. Probably neither are true. So that photo was taken around 1906, and he says that's the summit of Denali. And again, I think this is the subject to the world's first geolocation challenge. And there was a cool article 50 years later in Life magazine where their reporters, they claim to have found the actual source of the photograph, which is, spoiler alert, not the top of Denali. But it's 50 years later, so it looks a little different. But anyway, that's their conclusion, that this was a fabrication. And I mean, there's a lot of other evidence to lead us to believe that this is a fabrication. And the photo is cropped there. Anyway, they're probably right. It is probably the case that this is the Denali Range. Denali's north and south peaks are labeled with S and N, and the photo is taken actually in the region that is circled. If you can see the circle, here it's right down there. That. Okay, so anyway, I mentioned this because, again, prove me wrong. I would love to know, is there an older example of a ground level photo where there was some mystery about where it was actually taken? This one's more than a century old and has some historical importance. But yeah, if you have older examples, let me know. It's pretty fun to try and figure it out, right? A good brain teaser. So it has been gamified for a long time as well. And again, prove me wrong. This is the oldest game I can find out of this. This is from Condé Nast magazine. They had a running, it's exactly this geolocation challenge. You get a photo, there's actually some text associated with it, but you just have to say where in the world it was taken. And it's been a contest running for 40 years almost. I think there are probably older gamified versions of this, but I can't find it again. If you have a reference, let me know. So in this talk, now that we've introduced that's the challenge. That's exactly what we're going to be looking at for the next 20 minutes. I'm going to spend 5 minutes recapping the machine learning approaches to this task. I'm going to spend 5 minutes pointing out that humans are actually phenomenally good at this task, maybe better than some other recent papers thought. And then I'm going to spend 10 minutes looking at reasoning chains. That's the new thing. We're going to be asking experts and VLMs, not just to say where a photo was taken, but to give us an auditable trail of evidence. How did you know it was taken there? Can you teach me how it was taken there? Things like that. All right, but first, a whirlwind history lesson. So 20 years ago, for other research I was doing, we built, I think, the world's first data set of more than 1 million images for a computer vision task. And we were doing nearest neighbors in this data set in various, old handcrafted feature spaces. We would see things like this emerge, where if you take a query photo on the left and say, out of these, there's in this case 2.5 million photos that I've downloaded off Flickr, find me the closest photo, and you would come up with a photo on the right. And interesting things started to emerge, things that you didn't really notice with the normal 2006 era data sets, because they only had 10,000 images in them, which is like, these images are really similar, but in some ways they're also dissimilar. Does anybody know where these photos are taken? Some of you, somebody in this room is definitely from one of these cities. Spoiler alert, they're not the same city, actually. Prague. Okay, good guess. Well, that's cool. I mean, somebody's saying, okay. Here's the actual answer. It's not the same city, but it is startlingly similar, right? Similar architecture, similar layout. They're 380 kilometers apart. So they're not the same city, but they're the same country or region, sort of. So if you had a geolocation algorithm where you said, I want to know where that photo is taken, so you find a nearest neighbor, and that right one is your nearest neighbor, and you just guess its location, that's not a bad nearest neighbor algorithm. You're guessing the right country, at least, although the wrong city in this case. So again, this is the geolocation challenge. And I want to point out that it's not the same as instance recognition. Instance recognition means, have I seen this exact building or person before? You're not just trying to recognize something that you have seen before. Like in this case, they're not even the same city. You would hope instance recognition doesn't think these are similar because they're not the same instance. But there are instance recognition methods. They work super well, constellations of SIF points with geometric verification. And that might be helpful for geolocation, but we want to do more than just this in this research area. So we had the first paper with my then advisor, Alosha Efros. It was published here at CVPR a long time ago, where we scraped a data set of 6 million images and just had a simple nearest neighbor algorithm. If you want to know where a photo is taken, like this, okay, that should be easy for everybody. You just look at where the nearest neighbors are in a big data set and you guess their location. Well, that one's in Paris and that one's in Paris and that one's in Paris. This is super easy, right, for humans and machines. And if you look at the geographical distribution of these nearest neighbors, they're pretty clustered in Paris. I mean, it should be perfect. With better modern features, it would be perfect, right? But this was 18 years ago. But some photos are a lot harder, right? And you can't rely on instance level recognition to guess where this is. I'm going to go ahead and spoil this one. I'll let the algorithm spoil it. Here's where the nearest neighbors are from, with old features like SIFT histograms, color histograms. The photo is actually taken in Barcelona. The distribution of matched photos is not super tightly clustered around Barcelona, so didn't do as great a job here. But we're going to define a test set that looks like this, hundreds of photos that look sort of like this, tourist photos. These are the types of photos that we'd like to know the locations of. Here's another random sample of them. Notably, there's no like portraits or prominent portraits to preserve people's privacy. I mean, I built this 20 years ago, and it's kind of good that I did that because now we have this new modern problem of VLM refusal, right? Like if I have a photo that I want to locate and maybe I couple it with a slightly wrong prompt, then Gemini will come back and just say, no, I'm not going to help you do this task. So this refusal problem is something new that we have to compete with. Luckily, in all the experiments where we use this data set in modern era, the VLMs never refuse to do the task on these ones the way it did here. But you know, with a little prompt engineering, you can get around that and it will help. But you can't always prompt engineer your way around it with some models. We'll come back to that in a second. Okay, but anyway, we'll think about, you know, these are the types of photos that we want to geolocate. And back in 2008, with a big enough data set, we could get about 16% of them kind of right to the right region, which is good. I think it's better than the average person in this room would be able to do. And with the data set size typical of, again, 18 years ago, which is this, if you use the same algorithm, it would have been a pretty garbage algorithm, right? Like barely better than chance. So clearly this is a data hungry task, which is, again, a more reason why we should think, well, VLM should be awesome at this task now. They've seen everything. And I'm going to do a very whirlwind review of some of the state of the art throughout the decades that this task has been going on. So on that same benchmark where we started out at about 16% accuracy, in my thesis, with better machine learning, we did a lot better. Fast forward a lot to the deep learning era, where we're training conv-nets to do this task in some way, or training conv-nets and using them as a feature extractor to do nearest neighbor. They do a lot better. They're like double the accuracy of where we were back there. Fast forward a few years more to maybe, would we call CLIP the first foundation model? I don't know. CLIP demonstrated this task on this exact benchmark in the original paper. And it didn't set a state of the art. You see the number there, it's not state of the art, but it is zero shot. That was CLIP just doing retrieval with CLIP as an embedding network. And they only use a reference data set of 1 million images. I don't know if you can read this, probably not. In fact, this whole thing is kind of blurry. They only had a 1 million image reference data set. So it's actually pretty impressive. And methods that are now basically equal to the state of the art look a lot like CLIP plus fine tuning. So here's a recent work at CVPR a couple of years ago. I'm not going to look at this whole architecture diagram. I'm just going to point out that they're starting with CLIP and fine tuning it to be better at geolocation. And it does really well. This particular work demonstrated that they do so well by comparing to human experts. So that's what this plot from that paper, Pigeon, is showing. Pigeon's average error on some test set compared to humans in champion, master, and gold division. What is this? What is this business? How many of you know what GeoGuessr is? Well, that's less than I thought. I thought everybody knew what GeoGuessr was. Okay. So GeoGuessr is a game where you're doing exactly what we've just been talking about. And what they're pointing out is that even the best GeoGuessrs in their champion division can't compete with AI. And they had a really lovely demo where they took well, I guess what we could call a celebrity GeoGuessr player and competed against him. So this is Trevor Rainbolt. He's something of a prodigy at this task. And here he is struggling to figure out that this is Italy, and it's in fact Spain. He thinks it's Spain. It is Italy. And he was competing against Pigeon, who made the correct guess of Italy, and he lost this duel with Pigeon. He lost several of them, actually. Yeah, so well, it seems like machines have taken over yet another domain from us. Okay, but we're going to revisit this. Maybe this isn't a fair comparison. I don't know. But Pigeon and works like it, and that are fine-tuned CLIP models, they do great. Look where they are. They're like 70% of those touristy photos now, they're getting pretty accurate. So that's representative of the current state of the art. Those are recent methods. All right, I keep mentioning things like ChatGPT. Why don't we just ask ChatGPT where these images are? So we can do that. We go to ChatGPT. But the thing about ChatGPT is, like, the system card, or GPT-4 at least, says it's not going to be very good at this task. Right? That's basically what it's saying for privacy reasons, right? There's privacy concerns, but don't worry. We might identify the city, but ChatGPT is probably not going to be more accurate than that. Well, that's not true. So here we benchmark ChatGPT now, GPT-4V in particular, in gold, against some of the ones I just mentioned, Pigeon and GeoClip and GeoDecoder. What you see is that their performance at different accuracy thresholds here, they're very correlated. They're very similar. So, they're in some equivalence class, let's just say. But critically, ChatGPT is actually state-of-the-art for fine-grained geolocation. So less than 1,000 meters of error it's the best, beyond these bespoke models that this community has been working on. So yeah, pretty impressive, I guess. And by the way, we can go back to this one and just give it to ChatGPT, and it, again, less than a kilometer of error. It knows that it's Barcelona. It knows that it's the old parts of Barcelona, not like the expansion part. Okay, so then that's our whirlwind tour of machine learning approaches to geolocation. They seem better than human experts. Maybe that human expert just wasn't any good. I don't know. We'll come back to that. The human experts are actually amazingly good. And let's drill down on that a bit. So there's two big groups of human experts that have caught my eye. There's the open source intelligence people, investigative journalists like Bellingcat that do awesome work. And they have all sorts of work you can find on their webpage about geolocation. And it's important for war reporting, for confirming the authenticity of like social media videos and things like that. So they're human experts. The pool of human experts that we are going to be drilling down in this talk are GeoGuessr experts. So if you've never played GeoGuessr, this is what the interface looked like for one of the game modes, the one that's relevant for us. You're given an image, and you get to look at a map. You can zoom in on the map, and you put a pen down where your guess is. In this case, I guess that was Austria. It was actually Italy. And I get some sort of score or penalty based on how close I am. If it were a duel, I would be losing points if I were guessing farther away than my opponent. And the GeoGuessr claims to be the world's most popular web-based game. Surprising claim. I don't know if it's true. I mean, chess is pretty popular on the web browser too. The data that you see is the Google Street View data, which is a very broad distribution. It's most of the world. So that's where Google Street View data is. Here's another view of which countries are well covered in GeoGuessr. It's not quite the same distribution. And a neat thing about this distribution is it's always changing. There's 2 new countries in the last few months, Paraguay and Bosnia. Vietnam showed up within the last year as well. So it's growing, it's changing. It's a dynamic set. There's more than 1 billion panoramas here. It's something no human could memorize because obviously the world is big and visually diverse. But
what's it? French whole time Belgian.
oh, sorry, I will start this. But humans are really good. So this is the same person. I'm going to turn this down 1 notch, demonstrating in a very difficult game mode how good humans can be.
The French whole time Belgian whole time. Oh, is at least in Romanian thing. Yes. Wow, there's a blunder there. Do you go Jordan on this? Is this Jordan pavement? Surely with this kind of the leaf, probably. Yes, nice.
Looks like cheating, right? Well, here's some more.
Does this sound Korean sidewalk? Feel like a asphalt? Yeah, nice. Okay. Red white. Strike curve, Tunisia, UAE, makes sense. Tunis, I think it could be UAE. No, it shouldn't be UAE. I think this is good. Yeah, because there's a light outline. UAE, you have the other one. So, Philippines or India, is that Indo? Is it ever light? Wait, which one? This is Botswana.
Okay, again, it looks like magic, but for at least one of them, he was thinking out loud about the red and white curves and the outer lines. And wow, he knew that that was Tunisia. I mean, that was just, the man-made infrastructure here was correlated. That's the outer line right there. It would be yellow in UAE. So these are impoverished inputs, but they have learned so much about the natural and man-made tendencies of the visual world that they're doing way better than chance on these very difficult inputs. And again, you could go to community curated guides for any country. Let's look at Russia because it's an important country for GeoGuessr because it's so big. You can't just know that it's Russia. You need to know where it is. And within each country, the community has curated all of these things saying that for this geographic attribute, like where there would be sandy roadsides, here is where in Russia it would be likely to occur. And the same for vegetation, the same for different biomes, the same for man-made elements as well. Where are you going to see this area code in Russia? Where are you going to see this license plate registration type in Russia? Where are you going to see left-hand drive vehicles in Russia? Where are you going to see these bus stops in Russia? Where are you going to see mosques in Russia? But then also some definite overfitting. So the Street View capture process leaves some evidence in it. Like in this case, very degenerate, which way is the antenna on the back of the vehicle wound? Is it clockwise or counterclockwise? And that's what it's showing here. And these different antenna types have different geographic regions of support, right? So people have just memorized something about the capture process, which is not very appealing because that doesn't generalize, obviously. If you show a different photo of that region of Russia, you're not going to have that streetcar antenna in it. But still, these people work very hard to get very good at GeoGuessr, so they memorize what they would call meta as well. Not properties of the world, but properties of the capture process. And before I play some more, GeoGuessr is serious business. There is a World Cup in GeoGuessr. This is the third year that it just ran, the third year. And I'll show you a couple of clips from the finals of the World Cup. You know, prize money. These are professionals. They have sponsorships from esports teams and things like that. This is the semifinals of the European champion against another European.
I thought Peru. Yeah, I like Peru. That was my first. That's nice. This looks like it even there. I'm not sure which one it is. There.
We got 5 seconds left to go.
This is
He's
it.
gonna go Monterrey, Mexico. This is the game face. Because it's Indiana.
Dabre, a big name in the community. He advances to the finals where he plays an American.
That was quick. Because he's only open stuff in going on towards Hungary. Running out. That is pretty. The people. And round 4 of this NPC match. And we're looking north of our. And the main box in the distance currently holding both the USA and Canada. Around tomorrow. Not too confident once again. Talking with stars off again. It is. What should we have? Very, very good location. So later, oh maybe. Mexico have a fun dead rate. And oh, I'm not if they are both agreeing with that. He's thinking of Houston on because
And critically, Radu is a Georgia Tech student. So he was nice of us to help with this. And he's the best GeoGuessr player in the world officially and a professional at it. And an all-around nice guy. So he's been a great collaborator. And he and a few other experts are going to help us make a cool new benchmark with reasoning chains, not just geolocation accuracy. So if you ask Radu, where is this photo? Obviously he knows. This is easy for him. Does anybody know? It's not a very hard one for a GeoGuessr player. This has all the hallmarks of Ukraine. So it's definitely, it is Ukraine. And he can enumerate all the reasons that he knows that it's Ukraine. Well, actually not necessarily all, but all the critical ones. And not just that it's Ukraine, that it's southern Ukraine, because it doesn't have birch trees in it, for example. And he thinks it's likely that not just that it's Ukraine, that it's near Dnipro, which is true. The ground truth shows that he was right on the money. It is that city in Ukraine. And that's great, right? It builds trust that we can see the evidence that he used to make the decision. It helps us get better at the task if we care about that. But what if we ask, and I'll say a bit about the tendency of, if you ask the human experts to do this, then they often have course-defined recipes. Course as in like geographically course first the country, then the region, then the city, sometimes. They're not exhaustive. There's 1,000 different geographical attributes that you could latch onto. They can't list all of them that are present or not present. So they list the salient ones that support the decision. For example, in Ukraine, the road quality is poor in general. That's a piece of evidence that this community guide has written down. If you see terrible roads, maybe Ukraine. But he didn't mention that because he had other evidence that already narrowed it down. And then you kind of take the intersection of all these pieces of geographic evidence, and then that could be your guess. It's not like a mathematical proof in that the ordering is really critical. So if you're trying to generate and grade mathematical proofs, that's hard because you permute 2 steps and then the proof doesn't make sense anymore, right? It's not really the case here. It's more like we have a list a menu of evidence, and it's a little bit permutation invariant, maybe. And with Radu and other annotators, we developed these guidelines for writing down these reasoning chains. And really, this is more like encapsulating the tendencies that the experts already had when we asked them to do this task. Explain how you know that this is Ukraine. So we list, here we're just enumerating all the attributes that they often do latch onto, soil and geology, vehicles, language, and so on. Some things that they shouldn't address, like the street view coverage map. They shouldn't say that I don't think this is China because GeoGuessr doesn't sample much of China. And then, just some other guidelines for how they write. These are soft guidelines. This is more like codifying the tendencies that the experts already had when they were trying to make an auditable reasoning chain. Yeah. Okay, what happens if you ask ChatGPT then? So we can prompt ChatGPT like this, and we tried various prompts. Arguably we should give ChatGPT exactly these instructions. It wasn't necessarily helpful to do that. But we give ChatGPT a prompt like this, the same photo, and ask it, where is it? How do you know where it is? And here's what it says. And yeah, big picture up front, it does recognize that it's Ukraine. That's good. But there's some interesting things here, like in red, saying that, oh, there's some faint Cyrillic script. Oh, well, that would be a good clue that it's Ukraine or Bulgaria or Russia if you saw a Cyrillic script. And in fact, it can read some of that Cyrillic script. It can read the first parts of Zolotan Ashtra. But let's zoom in on the bus stop and confirm that. I can't read the Cyrillic. Actually, we can go in the Google Street View map. We can go to another view that's closer to that bus stop, look at the bus stop from up close. I'm not really seeing the Cyrillic script there, which is weird. Okay, we'll come back to that in a second. It also says that it did a search on Google Maps to confirm that it knows that this is Zolotan Ashtra. But I don't think it did. And we see this thing from other models as well, where they fake tool use. Gemini plausibly could be plugged in with Google Maps or something, but Quinn will do the same thing. It will say that it used some external tool to confirm things, but we know it didn't because it's an open weight model that we're running on our own machine. It didn't use Google Maps. So in red is a hallucination, which we've all seen from these types of things before, and in orange is fake tool use. There's a lot of failures in these reasoning chains. We'll drill down on more of them, but we want to benchmark maybe that says Gemini's very good at this, but to say that Gemini's not doing as well as it should because it's hallucinating, because it's faking tool use. And by the way, it's wrong about the city. It's not in the city. Its guess is not as good as our human expert, Radu. It seems like these models, we have this notion that when we have a reasoning model, that something like this is going on. There's a lot of intermediate work, evidence gathering, the gears are turning up here. And then based on all of this, you reach some decision like, oh, this is Ukraine or a specific part of Ukraine. And it seems like in the machines, when we ask them to do this task, it's actually reversed. Because it hallucinated Cyrillic text. Interesting. Like, it didn't hallucinate French. It didn't hallucinate English. Why did it hallucinate a text that perfectly correlated with where the photo actually was? Because really, it had implicitly recognized that it was Ukraine. Why? Through all sorts of reasons. Like, it's trained on 1 billion Google Street View panoramas. It's seen the statistics of the world. That just looks like Ukraine. So it knows that looks like Ukraine, and then it starts making up evidence about why that is Ukraine. That's not great. There's a term for this, rationalization. I'm borrowing terminology from my colleague, Mark Rydell at Georgia Tech. And I love this terminology because it captures that fact that you've made a decision and now post hoc, you're trying to rationalize it, which sounds bad, maybe, but I think it's not necessarily that bad. It's okay if the VLM explanations are rationalizations and they don't have any real introspection. They're not actually telling you how the VLM made this decision. But still, as long as the rationalizations are accurate, like they identify real evidence that the humans also identified, the human experts, then that's okay. It's still useful. It can still build trust. It can still teach us to do the task better. So regardless of whether they're rationalizations or reasoning, well, they should be better than they are. And actually, our human experts might be rationalizing as well. I'll just show one quick video of this.
Wait, should I do this or should I play it like deep fried? Wait, I'll play. Wait. No, this is fire. I still feel like this could be a little too easy, but I'll give it a shot. Just Brazil, 3-3. Two of them looks like, is there like a pyramid of mountains? Sure. Chile. River in Cambodia.
Okay, so he eliminated all the high frequencies from the image, so we can't even find all this evidence like certain lane markings or reading signs or anything, and it was still so easy. Because again, even as a human, he's played a million rounds of this, and so he just understands the statistical tendencies of the world, and he's guessing based on vibes. That's a term used in the GeoGuessr community, vibe guessing. So when we ask the experts how they know this was Ukraine, a lot of what they write down is rationalization as well, post hoc rationalization. But that's okay. It's still potentially useful. All right, I'm going to skip that for the sake of time, even though I've watched these clips all day. So we built a benchmark for this. From GeoGuessr, we sample 500 images like this, and we have our human experts predict the locations, but also write a reasoning chain about how they knew where that photo was. And we have 3 experts, Radu, Josh, and Tejas, who are co-authors of this work. They helped us do all this. And for example, here's one of the query images, and here's one of the reasoning chains from Radu saying how he knows that this is in Malaysia, for example, it turns out. Makes sense. We can also look at the accuracy of both the humans and VLM models at these same 500 images. So the ones in green, sorry, I'm getting feedback on this mic. Maybe it's not going to get better. The ones in green are ones where, in this case, Llama, not a very strong VLM, correctly guessed the location of the photo. And the ones in red are wrong. So Llama's not doing very well at guessing location, but Gemini is excellent, but not as good as the humans. Here's what Tejas did, and Josh and Radu. And we can put that on a plot. So this is error here, and these are the different models or humans. And we see the humans are still better than the best models at this domain. Maybe they're overfit to GeoGuessr a bit, but they're better, less than half the error rate of Gemini or ChatGPT. And Gemini is the best, it would appear at this. Okay. Let's look at the reasoning chain. So the humans are wrong sometimes. I mean, not often, but a few percent of the time they're wrong. Here's one of those cases where they weren't very accurate. Actually, they kind of got the country right. So here's an image. Here's how Radu guessed where it was. He correctly identified things like the poles indicating that this is a US territory, a tropical US territory. But that leaves a lot of places like Guam and the Virgin Islands and Puerto Rico. And so he guessed Virgin Islands. It was actually Puerto Rico. So it's hugely far away, actually, although it is still a US territory. So in some sense, Radu's guess was wrong here. It's rare, but it happens. But all of the evidence that he listed, I think is still trustworthy. That's still true statements about the image and about what narrows down the location. So, so in some sense, we use all the reasoning chains. Even if the human gets the wrong location, we assume everything here is a good reference to use as a benchmark. And what do the humans mention? Well, here's the different types of geographic attributes that they focus on. So infrastructure, things like power lines and lane markings are the most common. Vegetation second most. And again, here's meta, that category of things that aren't a property of the world, they're a property of the capture process, which isn't great, but it's in there. Now, we want to make a benchmark out of this, so how do we score it? So, for example, we give this image to Gemini, we give it the appropriate prompt, and it gives us this reasoning chain about how it knows that it's in Malaysia. It's done a very good job here, actually. And we have human reasoning chains, actually 3 human reasoning chains, but here's one of them, Josh from one of our experts. And he also, says it's in Malaysia. It says a lot of the same things, but we need to be able to quantify this, give a real valued score to how good is this reasoning chain. And we're going to use an LLM as a judge approach. We tried VLM as a judge, but we're going to use LLM, as in we're going to hide the image. And we're just going to look at these 2 bits of text, and we're going to use an open weights LLM to give us a real valued score for how good this is with respect to this. And I'll break that down into more. But again, we did try other things like VLM as a judge, where the VLM gets to look at the image itself, but it didn't perform better. So anyway, the rough idea is that for every point here, we're going to ask how well supported is that by the human expert reasoning chain. And we're going to have an LLM do that. Again, we're going to ask Quinn with some appropriately tuned prompt to give us a real valued number for how well supported it is. Maybe it says 0.75. And we're going to do that for every one of these points. And again, it can match to many points on the right-handed side. That's fine. And we're going to accumulate all of these real valued scores and just take the average of them. And we'll say that that's the precision. Of the things that Gemini said, this is how well supported they were by the human. That's good. You want that to be high. You want it to be 1, but it's not enough because Gemini could just say one thing that it's really confident about and leave it there. So we're going to go the other direction as well and measure recall. For everything here, we're going to ask how well supported is that by the statements here? Just use the exact same function call, but reverse the inputs. And then that will give us a recall score. And then we just take the harmonic mean of those, the F1 score. And that's a high number. That means that Gemini reasoning chain was quite good, and it was. It agreed quite a bit with the human, but they won't always agree that much. And to validate that we can use an AI agent, an LLM, to score these, we have humans score things first. We have humans grade other human-human agreement. So we have 3 annotators, so we can leave one out. We can have Radu grade Josh versus Tejas on a particular image and do this exact same, work through that same algorithm by hand and give scores to human agreement, to Gemini to human agreement, or to human to hallucination. We have another, I can't go into details, but we have one input that's just pure hallucinations. We want this to score low. And we can check, well, if we ask Quinn to do the same task, how well does Quinn agree with our human graders? And pretty good. We would like these things to line up exactly. They don't line up exactly, but pretty close. But using Quinn as a grader means that we can do it at much larger scale and grade all these other things as well. But we see there's quite a range. We see, first of all, that humans and the best VLM, there's still a big gap, which just means that the VLMs are making stuff up, missing stuff, getting stuff wrong. We see that open weights VLMs are much worse than the closed weight VLMs. The open weight ones aren't much better than the just like pure hallucinations. Here's a plot of accuracy versus reasoning chain score. They're correlated. But again, the humans are better. Humans are better in every way. And there's sort of these equivalence classes of closed weight VLMs and open weight VLMs. All right, I'm going to go quickly here and just show some examples of, to wrap up, of where the VLMs go wrong. So if we ask, who do we ask? Gemini, where this is, it gets it very wrong. It says that this is Egypt, which is fine. It's a tough image, but it just makes up so much stuff. Everything it's saying here is a hallucination. The image is actually in India. And so that's all just made up. And then this is not made up. That's a true statement. It's a dirt track running along an irrigated green field, a very common feature of rural Egypt. It's like, what? I mean, yeah, it's a dirt road against a field, but that's a very common feature of everywhere on Earth. So it's just like a vague geographic property that it's somehow saying is discriminative when it's not. So that's not very good. Another failure case is that the VLMs, despite us giving them very high resolution images, they don't see very fine scale details. Is anybody good at geoguessr know where this image is? You can know it. You can narrow it down to 2 countries pretty easily. Sweden is a good guess. Gemini says that it's Germany. And it says, oh, I know that because look, I can recognize this very specific type of bollard. Look, I'll even give you the name for it. But it's not a German bollard. It's a Czech or Slovakian bollard. It happens to be Czechia. And here's what a German bollard looks like. You can see they're different. Like this one has 2 reflectors and this one has 1. And a human sees that and the VLM missed that. Again, even though we give it the 2 or 4 megapixel image, like the detail's there. And then one last one. Where is this photo taken? It's got a really prominent, beautiful eucalyptus tree there. So it makes you think Australia, I feel like. I was just in Australia, so I think Australia. But all of our experts confidently say, oh, the power line tells us it's South Africa. The insulators tell us it's South Africa. It's South Africa. What are they talking about? Well, if you zoom in on that power line, you see what looks like birds perched on it. Those are the insulators used in South Africa. Again, if you look at the community guides, you can see other examples of this. So the human experts immediately see this really fine scale detail. It's completely diagnostic. We 100% know it's in South Africa as soon as we see that. Eucalyptus trees are not native to South Africa, but they got planted there. Whereas the ChatGPT says, oh, it's Australia. I mean, I can see why it says it's Australia, but then it makes up all this evidence to support that it's Australia. It even points to the power infrastructure and says that it's Australian. So there's a gap there, and it's cool that our benchmark could capture it. I'm about out of time, so I'll just say that there's this gap remaining here between experts and the VLMs. And the VLMs are well positioned to do well at this task because they have encyclopedic geographic knowledge. They've seen more images than any human, but they're missing fine-grained details, and they're missing the linkage between language and visual content. I feel like these models are a little too language first and not getting everything they can out of the images. And to circle back to this workshop a bit, language is like newly way more important to all of us. I feel like language was a burden to computer vision for decades, Like whenever language showed its head in computer vision, like defining the taxonomy of ImageNet, that was annoying. It's like, well, who cares about language? We care about images. But we should maybe expect our models to talk to us, and we should be able to grade how well they're talking to us. Natural language, the models handle it so well, we should embrace it maybe. And it is good that LLMs are pretty good grading mechanisms as well for this. So if you want a method that communicates in language, then it's easy enough to have humans annotate in language. It's easy enough to have other LLMs grade in the language. It is good that all of that is feasible, I suppose. And again, it speaks well to the goal of this workshop, where we hope that experts can define taxonomies and annotation instructions, and the AI agents can understand them. Yeah, it seems plausible, I guess. All right, that's it. Thank you guys for your attention. I'm happy to answer questions.
Thank you, Professor James Hayes, for the very interesting talk about geolocation, and we have time for maybe 1 to 2 questions. You got the microphone. Yeah, please.
Thank you. How do you think you would fare if we include scenarios where no reasonable guess can be made? Like the image of the tree with a lot of the sky, it's not fair for anyone to guess that, right? Could you use that to define more scenarios where models have a say, where the layers are going by lot of things?
Yeah, that's a good point. So first of all, our benchmark was all sort of mainstream GeoGuessr samples that were all, well, you saw the accuracy. They were all locatable. But that's a good point. If you intentionally impoverish the input so that any output could only be a hallucination, then yeah, maybe that would be one part of your benchmark. And maybe that makes sense to have like an impossible part of your benchmark, just so that you can penalize all the hallucinations that will pop up. Because that is a fundamental problem, is that it's hard to penalize hallucinations, because the AI agent could say something. It could be something that the humans didn't say, but it could still be correct. And it wasn't a hallucination. It was just something like amazing that the humans didn't even know about. We didn't see a lot of that, but it is hard to penalize hallucinations. But yeah, that's a good idea.
Please.
Thank you for wonderful talk. I find it very fascinating with even humans making the prediction and then rationalizing it. I was wondering, is there a difference between whether you get a human guesser to predict and then rationalize, or if they kind of reason as they're making the prediction at the same time? Does that change the quality of it, or is it the same? You might have said it already, sorry.
No, I didn't. And if I have time, I'll show a very brief video. I think it's impossible to get humans to do that, because they so quickly reach this decision. I'll just so in this case, blink and you'll miss it, because he's going to show it only for 100 milliseconds.
Not even that's a fair enough. And thank you for realizing that. It's Ireland.
The thing is, their decision is too fast. Like their vibe guess of where it is too fast that you can't. No, I think that's hard to do. For the BLM, could try to do that. You could try to put them in an evidence gathering phase and then have another stage where they distill this down into one decision. But I think it's tough. I think it's a good idea.
Thanks, Professor James Hayes again. Yeah, I think.
Oh, you're still sharing, James?
And you can't kick me off.
I think it just did. Share. Right, beautiful. Looks like it might not be sharing the whole screen though. Oh, it is?
Yeah.
All right, good. Perfect. All right, great. Great to be here. This is a pretty exciting workshop. Hot topic these days. I love it. So my talk is entitled "All Your Embedding Are Belong to Us." I hope you know what that's from. If not, you'll soon learn. But this is in fact part 2 of a 2-part talk. So the first part I gave at 1 o'clock today. Before I begin, I want to thank my collaborators, both from Michigan and Vauxhall. And also, I just have my LinkedIn down here because that's my job at Vauxhall now. We're 10 years old, and I just have to post every day. So find me and let me know if you want me to post about anything. So if you know what this is about, right? So this is from an '80s game, late '80s, early '90s game called Zero Wing, and there was an error in the translation from the Japanese to the English version. All your base are belong to us. And I just thought it was so fitting for embedding. And I've been in this space. Wait a second, we can't just scale. Scaling is not the answer to our AI problems. We have to actually study and understand. And in fact, if you think about it, it's kind of like a translation problem as well, right? Like we see the embeddings, they're working. We know that we can play the embeddings, if you will, and use them, but we don't really understand what are in those embeddings. And yet there's such rich structure in these embeddings. So this is just different embedding spaces will be rendered after a 2D UMAP projection on the right-hand side for a small form factor open source robot that Hugging Face released that we're working on. This is actually in the Vauxhall 51 robotics lab. And you can see as we're interacting with some of these embedding spaces, in clusters of embedding spaces inside of this app, that they really capture certain types of quantities, qualities that are present and captured automatically by these VLM models, by off-the-shelf VLM models. Even here, like the structure of the robot arm was ever omnipresent, right in this subspace of the embedding space. This actual interface here, just to make sure that I do my job, is from Vauxhall 51. It is the open source 51 toolkit. I'll show you how to get to that if you want at the end of the talk. So in the first part of the talk, I gave two papers we've had in the last few years about really demystifying that underlying structure in the embedding space. The first one is, do the embeddings contain information about what we should label? And so this is an instance of the course set selection problem, and it could save you orders of magnitude on your annotation budget. Importantly, Vauxhall 51 is not an annotation company. We never were an annotation company, mostly because I just thought annotation was becoming a commodity, and we were going to be able to use foundation models as early as 5-6 years ago to do this. It's taken a long time to get there, but I think we're really there. So course set is one way to do that, right? Like, okay, I have huge amount of unlabeled data. Let me go and find the subset of it that I want to label first to then go and train my downstream model. All the state-of-the-art methods are essentially outperformed by random, except for one. Course set selection is really hard. There's so much. My explanation, someone actually asked me about this in the hall. So I think the embedding space is so rich that there's kind of like an equivalence class of 10% subsets of the data that all get you the same downstream performance. And so getting to that equivalence class is very easy through uniform. But outperforming uniform is possible if you think about the embedding space structure properly. So we have this paper called Z-Core, which uses a Monte Carlo-like sampler over the samples in the embedding space to be able to compute an importance score, fully unlabeled data, and then ultimately map that to outperform random at scale on a larger data set like ImageNet, and also outperform T2DS, which is the highest performing method we're aware of that for course set selection. And it is exceptionally computationally expensive. It actually trains tons of models to compute how much backprop contribution each sample has and computes importance like that. So that was one interesting mystery we kind of dispelled earlier on. Then the second thing I talked about earlier was about what do these embedding structures tell us about the difficulty of a data set? Would it be possible to compute how difficult the data set is, labeling only, say, 100 samples per class and never training a model? Is there enough structure in the embedding space to actually do that for us? And the answer is yes. So we introduced this notion of reconstruction error ratios. So delta C on XC, XC is a sample here, delta C is the reconstruction error with a very shallow autoencoder, trains in 5 to 10 seconds on 100 samples separate per class. So the ratio of the in-class reconstruction error for a shallow autoencoder to the nearest out-of-class reconstruction error is highly informative. This chi statistic is kind of like a probe on that sample. If that ratio is significantly greater than 1, it means there's some distractor class other than the ground truth class that represents the sample well, i.e. there's a mistake in the label for that ground truth class, right? So you can go and throw it away if you wanted to. If that chi statistic is very low, it's a strong indicator that that sample is distinct. Now, if you look at the distribution that's an embedding space, a two-dimensional UMAP embedding space on, I think, just ResNet 18. So these are class labels on the left, embeddings on the right. You can kind of see naturally lower scores are purple, higher scores are yellow, with the two classes on the right there, that as you near the class decision boundary, obviously they get closer to 1 because there's a little bit more confusion. That's just an example, but you can also see many yellow points in the centers of other classes. So there's something about that chi statistic that is interesting. And there is indeed. So we introduced this notion of a data set determinant. You can take the expectation of the chi-score, i.e. the average chi-score over all the samples in a data set, and it actually outputs a meaningful measure of the classification difficulty for the whole data set. And it correlates strongly with 1 minus the accuracy on the top performing, state-of-the-art, deep net, or whatever classification you have. So image on the right, horizontal axis is that 1 minus accuracy on a log score, log scale, for the best performing data we could find on each of those data sets. And the vertical axis is that chi-bar statistic. You can see bottom left, easy things, both for chi-bar and 1 minus accuracy, things like MNIST, CFAR10, Euroset. Top right, much harder things. Places 205, describable texture, SUN 397. Correlation here is 0.802. So pretty interesting, I think. And furthermore, these RERs actually decompose classification difficulty independent of the number of samples you're using to train those shallow autoencoders. So the horizontal axis here is the number of samples you're manually labeling to feed into those shallow autoencoders to then go and compute the chi-bar on N. And you can see we can fit these functions all the same form. And what this ultimately means is that assuming the distribution of samples we have matches the actual distribution of the data set we care about, getting more data and labels is not going to actually help or make the problem any easier. And so we should be able to map that number of samples to the classification scores we get. So those were 2 highlights from earlier today. What I really want to talk about today, though, is some very recent new work that we call the label imitation game. In fact, it's so new, it's not even on arXiv yet, which I know is risky in this field, but here it is. It's in review, and hopefully we'll be talking about it soon, even more commonly. So this is about, this takes VLM type models and says, can we use them to do auto labeling or pseudo labeling? It's commonly called in ML, right? Like basically take unlabeled data, apply VLMs to it, get a labeled data set that we can then go and downstream train. Most people say, of course it's going to work on easy things like cars and trucks and buses and whatever, and it's going to totally fail on hard things like that only have 10 samples or 20 samples. That is the core problem in pseudo labeling for value, right? And we'll show you how we can overcome that problem. And so high level, and I apologize for the slides. There's a lot of like snips from papers and so on. These are not polished slides, but it should be an interesting talk nonetheless. So foundation model pseudo labeling, popular, and it should be used in general, mostly because, again, annotation's a commodity. Like, why are we spending so much money, collectively across the globe to label the same things over and over again? So we think of this as labeling data strictly via zero-shot inference. That should enable massive scale for data engines. All right. Key challenges, though, are that, as we heard in the last talk, even to some degree, like foundation model performance is undermined by hallucinations of various forms. And these hallucinations would then go and degrade downstream performance, right? So you get your auto labels, and you want to go train a detector, if it's polluted, then your detector will be useless. Unfortunately, you can't just threshold based on confidence. If you threshold based on confidence, many of these VLMs are very confidently wrong, not infrequently, and it's a problem, right? So on the left hand inside here, this might be I forget the VLM that was behind this. But anyway, that's clearly the front of an airplane. All of us can tell it's the front of an airplane. Plane says train. That's a statue, not a person. That is not a teddy bear by any means. That's the Baltimore Orioles mascot. That is not a bus. It's a van. I'll give the last one maybe. It is a van, but it's mistaken as truck. So that gets to that, what James was saying. Like, language is really messy. The ontologies we map language to in these closed world problems are painful. And these models don't have a way of really bridging between that. So this motivates the need for a post hoc judge that can take the output of these VLMs and throw some away, right? So we think of this as pruning the pseudo labels, pruning the auto labels. And ideally, this would happen with no human supervision, no changes to the underlying VLMs, and no changes to the training pipeline downstream. So really just something that can take off-the-shelf VLM, apply it on the data, and then get a better data set that will lead to a higher MAP score. That's the goal we have here. And the challenge here, though, is it has to differentiate between accurate labels and hallucinations, right? Like if you're familiar with the Silicon Valley show, hot dog, not hot dog, like if we can get that type of a test for each class that we care about, in some sense, we would be in good business. All right, and so this is the key idea here in how we do this, is at the bottom of the slide, actually. So we will basically sequence a set of pseudo-label tokens. So these are embeddings from the VLM. Some we trust. We know that they're kind of like in class or in domain that we care about. We'll feed these into a judge, which we call a Turing test network. And then that judge will output a sequence of accept or reject, live, die, if you in that way. And this will hopefully, the judge, it's not an easy problem, right? The judge has to overcome like class partialities, right? Like maybe for some reason there's a bias toward cat instead of dog in this data set, and snowman versus unseeable snowman across these different data sets. All right, so ultimately that's the basic idea that we're going to be looking at in this work. And if you don't remember anything else, it's okay, because the paper will be coming out, and take some time to learn these things. So there are three basic pieces. First, I'll introduce the label imitation games. So this is a framework formalizing label pruning as an adversarial interrogation between a judge and some candidate labels. Then I will introduce the Turing test network, which is a lightweight model that evaluates the semantic logit, or like the plausibility given context of labels within a data set wide reference set. And it will do that without knowing apple, cat, dog, or like having any human. We don't need to know the class. We just need to basically localize in the embedding space, build a kind of like a local implicit manifold to make those decisions. And then we'll show we can actually deliver zero-shot task transfer by playing these label imitation games. In other words, training on massive classification data sets and then applying the same TTN, same Turing test network on a detection problem. Fully different type of task. All right, so pseudo label. So given pseudo labels y hat for an unlabeled data set du, the goal in pseudo label pruning is to select the label subset y tilde, which is a strict subset of y hat, such that the F1 score is maximized. Now, this is different than the Z-core paper, where we set a pruning goal and we drove how much we were going to throw away based on that pruning goal. Here, we set a goal, we want to maximize the F1 score, and we'll keep as many data samples as needed based on the pruning goals for pseudo-label pruning. The goal here is to increase the precision by rejecting noisy labels while trying to maintain the recall as much as we can by accepting the accurate ones. All right. So downstream models will ultimately be trained on that subset D tilde. But we have a secondary goal, which is to minimize the problem of inductive interference, right? This is what I was saying earlier, right? Like as you get pseudo labels that are bad, poorly labeled, or even just messy in some certain ways, it can actually interfere with your downstream detector. So it is a secondary goal, which we will show results on here as well. Okay, first, so label imitation game. This is inspired by the classic Turing test. As you all know, the Turing test evaluates a machine's ability to exhibit intelligent behavior that is indistinguishable from that of a human. Is it a human or is that a machine? And so we motivate that, we map that onto label pruning. Label imitation game is defined as evaluating if pseudo labels are indistinguishable from those of a human annotator. That's enough for us. As long as they're in that distribution, in that space, that's okay. The game players here are ideal labels, candidate labels, and the judge, which in this case will be this Turing network, right? In fact, a little digression, we don't work directly on the labels of the samples since we're in the world of transformers and so on. We actually work on the tokenization of these things, and we'll train our own tokenizer. The details of that really don't matter critically. There's a kind of like a generalizability to the original labels and the data. So it's more like a token imitation game, but there we go. So, okay, first, there's the pseudo label game, imitation game 1, right? So given a set of accurate label tokens G star and pseudo label tokens G hat, identify which tokens are from the pseudo labels, right? That's kind of like a one class imitation game that we want to focus on. So we will need labels for this. And ultimately, we will train the initial TTN on pre-existing classification data sets and use the labels from those pre-existing classification data sets. All right, so that's the first label imitation game. The second one plays a different role. It's OCG, or out of category game. So given tokens with a target category, C star, and tokens from some other category. So now we have two categories in play. So C star and not C star. Identify which of the tokens are out of category, right? So OCG, it enables us to basically massively expand the number of training examples we can pull from these classification data sets to train the Turing test network that will motivate. Importantly, though, in neither of those cases do we need to know the identity of C star or not C star. We just need to know their relationships. All right, Turing test network. This is a relatively simple and contemporary network that learns to be that judge. So we begin with clip embeddings, which is frozen. We do not fine tune, train, or touch clip in any way. We do train a custom tokenizer. The details are on the right here. Although we do train it, it really is kind of like off the shelf. There's nothing special in our like empirical work that went into that customization. And then we have transformer reasoning blocks that evaluate those tokenized data points and then learn to output the accept or reject logics. Relatively straightforward incarnation here. And that TTN plays the role of the judge in the label imitation game, and it learns to, given a token sequence, output accept or reject tokens based on what type of game we're playing. So when we're training it in the classification world now, we use input training sequences that have only 10 reference tokens. So those are either all in class if it's a label imitation game 1, or 5 from each if it's a label imitation game 2, and then 1 candidate that's out of class for equal from class distribution of like flip a coin class distribution. We actually train our batches through using different sequences of the label imitation games just to vary the complexity over which the TTN must be exposed to. All right. Classification TTNs. So we train and test on 8 diverse classification data sets. We train 1 TTN across all of these data sets. So it's not a per data set TTN. We inherit low-res robustness, if you will, or small object robustness via some small, like CVPR'100 has very small images. So we just inherit that because we're training only 1 TTN across these data samples. We take 80% of the images or the data samples from each of these data sets as training data and use the remaining 20% as validation. And then collectively, we find a validation accuracy of greater than 94% on average and on most of the data sets. The only one that's less is CVPR'100, which is the one that has the really small sample. So it's, in some sense, the hardest one in this case. Now, if you map that onto when you go buy some annotations from an annotation provider, generally they're going to tell you 95% accuracy is the best they can do. In my experience, it's much less than that, in fact. But this is already able to there's no human involved yet, right? We're just taking encyclopedic knowledge off the shelf that we already did in our community for the last 20 years and mapping that into this one network that can do these judging. All right. But even more interesting is that we can transfer that classification performance to another problem, detection, right? So in this case, no supervision at all. We incorporate what we call self-referential pruning. So we'll take an ideal reference set from our classification data that has like the highest 1,000 highest confidence pseudo labels. Oh no, this is for the in-class data for a detection problem. So we use the confidence that the VLM outputs here, but then we do this self-referential pruning. Some of those high confident labels can be thrown away by the judge that we're using here, right? So that's not going to confuse the downstream performance there. And then we'll evaluate all candidate pseudo labels on that against the reference set, again, including those ideal ones. And then we aggregate accept reject logits over multiple games so we can get kind of like an expectation, if you will, over whether or not we should throw it away and find that we're able to get performance. In fact, there is an emergent behavior that comes out of this, right? So remember, TTN is trained only on classification data, and now we're applying it here to a detection problem. So we would expect semantic flaws to be captured, right? Like it's not a train, it's an airplane, it's not a person, and so on. But we also actually find an emergent behavior for spatial errors to pop out as well. So here, that is definitely a water bottle on a bike, but spatially, it's not sufficiently overlapped with the bottle to be correct. Same thing with the boat, same thing with the tarp, or I guess the tarp goes across the whole truck. And in the one on the right, in BDD, there are actually 2 cars in that box. So that's not a correct label either. Right, so this was an interesting emergent behavior. All right, so however, there do exist labeled detection data sets as well. So we would be naive not to also try to use them in this data in this project. So we do task-specific fine-tuning, so detection-based fine-tuning, and we can train a model TTND that takes 100 or less human labels per detection class, and along with VLM VLM outputs, and then fine-tunes our TTND model in this space. And we're able to demonstrate relatively good accuracy as well for the detection problem. All right, so how does that map to other performance here? The downstream performance is really what matters, right? Like our ability to label data is just labeling data. We've been doing that via humans for a while. Only if those resulting models are useful does this become useful. So we introduced the benchmark last summer. It's on archive that uses VOC, COCO, LVIS, and BDD for doing auto labeling analysis. I encourage you to check it out. It has some interesting metrics that are not commonly used in the auto labeling or pseudo labeling space. But it also has data sets with very different characteristics, right? Like VOC and COCO, we're all relatively familiar with them, and they're kind of straightforward and simple. But LVIS has like 1,000 classes. Some classes only have a couple dozen at most samples in it. And BDD, despite it being not new, is still pretty challenging in our space. So it also has very unique visual distinction. So as far as evaluation goes, TTN and TTND consistently increase precision and with a minor recall reduction across the 4. Oh, this is across the different embedding spaces that we're using. So this is more like an ablation result here. In these graphs, orange is TTND, the magenta or like the blue one in the middle is TTN, and the black is AL. So we're seeing in the bottom row, precision is increasing across the board. And in this case, on the top row, the recall is not dropping significantly. 4th row down is the F1 score. We also note that TTND increases F1 in all data sets, and TTN actually also does increase it on all but on BDD, which is great. And maybe one can infer that for actually scoring in these types of challenges or whatever, precision gains trump recall loss in this work. So how about downstream impact? So in this case, we trained YOLO, 11N detectors per pseudo label data set separately as the downstream object detector. And we find that TTND is able to improve MAP50 scores across all the data sets in practice here. Interestingly, though, so before we get to that part here, so we also, this is an encouraging result, right? Like one does not necessarily expect to basically stir a magic pot and be able to improve downstream detectors with no humans really involved yet, right? So this was interesting. So we wanted to know then, how good can we do? Like, what is the upper bound on performance here? So we introduced this notion of an oracle label imitation game that always gets it right, right? So we know on all these data sets, we have all the labels, right? So we can just always get the judge, have the judge be correct. And we find that TTND closes 40% of the gap from the raw auto labels, raw VLM outputs, up to the max, up to the upper bound. So there's still room for growth in this space if anyone's interested in the problem space. All this code and work will be available online as well. But more interesting, which is interestingly here, is that we notice what we've begun to call category revival. So these are the classes that are in the tails of the distributions that are greatly imbalanced, that basically have almost no recall, like 0.054 the chair, 0.133 the mean, for example. On BDD, the car, or the motor, 0.016. Like these classes just don't get detected by VLMs. Yeah. These classes just don't get detected by VLMs, right? They're just not happening. Yet TTND is able to increase their score relatively by 44%, i.e. revive those categories and save them, still without needing human labels. But even more interestingly, though, for these particular subset of classes, the oracle increases by 432%, which means there's massive value to be gained if we can figure out which to run and which to save. All right, great. Thank you. So I think there are many secrets in contemporary embeddings, and I believe it's a great problem area. So if you want to chat about that, anytime, I'm interested in doing that. Just to summarize, though, today, I introduced the Turing test network, the label imitation game, and noted how we can effectively do pseudo-label pruning with no humans involved to not only rescue classes, but also lead to general MAP50 improvements downstream. This is that little stub. If you're interested in playing with 51, if you have never used it, here's an example video, or just pip install 51, or we'll be at booth 309, or here's a QR code to talk to us. Thanks for your time.
Great question. Looking forward to your paper when it does come out. I'm curious how that initial labels, like how representative they have to be of the object class for this to work. Like if I did a really bad initial set, like all red apples and then expected it to find green apples, can it kind of build apples, or is it stuck in that?
So we have only trained one TTN model. I mean, tongue in cheek, right? So like we've trained many of them, but like there's one TTN model that we use for all these results, and then one TND model. So my view, I mean, this is pretty new work, so I don't have like a deep theoretical understanding of what's happening. My view is that it doesn't matter, actually. Like there's something about these local manifolds in these embedding spaces that are being trained now that it is latching onto. And independent of where that is in the embedding space, it's able to properly, tune in. Yep.
Thank you. Thank you.
Yep.
Do you want to go?
Yeah, sorry for interrupting.
No, it's fine. Yeah, that's good.
All right.
Okay.
All right. Hi, Professor Petro. Can you hear us?
Yes.
Sorry, I think my mic is muted.
Yeah, I can
Sorry.
hear you.
Oh, great. All right. Please feel free to share your screen. I'll give it time to give a brief intro. So our next speaker is Professor Pietro Perona, and Pietro is a professor at Caltech. He is a thought leader in computer vision, CV for scientific research, data annotation, and human in the loop, and so on. A lot of things. So let's welcome Professor Pietro, please.
Hi, everyone. Very glad to speak here. Is my voice audible? Is this good volume enough?
Yes.
Okay, that's great. So I cannot see the the room, but I wish I was there. I couldn't. So hi everyone. So I thought today I would speak mostly about my motivation for this topic, which is very high, to affirm that it's a great topic. So I'm glad that the organizers proposed a workshop, and I hope that the workshop grows, and also to propose a few metrics for success for this workshop to see where we can go with it. And so I'll start with a little story that tells you how I came to be interested in this topic. And this starts just before COVID, when a bunch of honeybees came into my backyard. And I found this swarm of bees. I thought I would try to capture it and put them in a box. And in order to do that, I called my friend Chuck, who instructed me on how to get the bees into a box and then how to take care of the bees. And quickly enough, the bees became from one box, 2 boxes, and then 3 boxes. So I had 3 colonies, and every year they produced a lot of honey that you can see here. This is part of the honey I got one year. So it's a lot of fun. You learn a lot of things about nature by beekeeping. I don't know how many people in the room are beekeepers, but it's something I recommend. As part of the training, I learned that there are some parasites of the bees that you have to take care of. And so one is called Varroa. And you see here one of many articles that appear every now and then in newspapers saying that Varroa is causing damage to bee colonies and one has to be very careful. And if you look at the Wikipedia page, it's called Varroa distractor. So the name says it all. People don't like him because it's a mite, and the mite is quite ugly. It lives on the back of the bees, and it sucks fluids from the little larvae, and so it causes damage to the larvae. It's not a good thing to have in a bee hive. And so I became very concerned, and I started looking at my bees to see if I could spot this parasite. But of course, it was very difficult to see. And people told me that it's not frequent to see it because it's small. So what I thought is, and also they told me that even if you have very few, the population of Varroa can explode quickly and damage your colonies unless you're careful and you take very quick action to help to prevent it from being there. Let me put on my face. Okay, so I thought, okay, well, I live in I'm a computer vision scientist. I should just take lots of photographs of the combs, which are these structures in which the bees build their nests. What you see here is a bunch of bees. I think that there's a queen somewhere here. And some of these bees have varroas on their back, but of course it's very difficult to see it. And so being a computer vision person, I thought I would take lots of photos and use computer vision to find the varroa mites. And so how would I try to solve this problem? And so now we are back in 2019, 2020, and very still influenced by supervised approaches to computer vision. And so, my mind goes back to 2004 to 2004 when, with my student Feifei, we collected a bunch of categories, which are called Caltech 101, to train different image classifiers. I think, okay, I have to collect lots of images. Now, as you know, Feifei went on to collect ImageNet. And so here is 1,000 category, 1,000 images per categories. That's good enough. And indeed, there's a picture from the research of my student Sara Biri, who is a co-organizer of this workshop. And and what she does here is she shows what is the error rate, which you see on the y-axis. Let me see if I can get my mouse. No, I can. Yeah, I cannot show my mouse in the slide. But the y-axis is the error rate, which you see goes from 1% at the bottom to 100% at the top, as a function of how many training examples there are per class. And here the classes are animals that you can find in pictures taken by wild cams in Southern California. And so as you can see, the top left point, red, is a badger, of which we only have 5 training examples. And so the classification error rate is horrible. It's 80% or 70%. But the good news is that if you take more training examples, you can drive error rates down to about 1%, which you see on the bottom right. So you have opossums are at about 2% error rate. And these are classification errors, and they're not detection errors, but as you know, they're related. Okay, so that's good news. So if we get enough training examples, we can drive error rates very low. However, the bad news is, as you can see, the x-axis is a log scale. To get to 1% error rate, you have to have 10 to the 4 training examples. That's not such good news because you need many. And now we're in a detour. And so you know that you have many categories in the world. There are many millions of categories. There are 8 billion people on the planet. There are maybe 50, 80,000 Chinese characters, lots of different types of shoes. There are a million or so animal species, et cetera, et cetera, et cetera. And so if you wanted to collect 10,000 images per millions of categories, you're in trouble. It doesn't scale very well. And so here we start smelling that there is a good motivation for the reason why this workshop was put together. Now, at the time, or a little bit earlier, Serge Belonge and I started thinking about how to collect enough training examples for lots of species of plants and animals. And so we started collaborating with 2 communities, iNaturalist and Merlin Bird ID. These are 2 communities of naturalists, and we built for them. In fact, the we includes Grant Van Horn, who was my student, and now he's a professor at UMass Amherst, and he's the guy who did all the work. And so what Grant did, he embedded with these communities and built the computer vision backend for the apps that you can download to your phone. And I would encourage each one of you to download iNaturalist and Merlin Bird ID. Merlin Bird is on the left and iNaturalist on the right. And they recognize plants and animals through photographs, but more importantly, by interacting with the community, they can learn from the community to classify new species. And so here you have a heat map from a couple of years ago showing the density of observations in iNaturalist. And here you have for the last 12 months, how many observations have we collected? You can see that we've collected about 350 million observations, 350 million observations. And the red curve shows the research grade ones that are about 200 millions. And research grade means there are enough annotations per photograph that the photograph can be used in a training set. Okay, so this is good. We have ways of collecting tons of images. The trouble is that it's a long-tail distribution, and for most species, we don't have enough, despite the fact that we have so many. And so now we go back to the Varroa problem. And so this is an image of a zoomed-in version of the image I showed you before with lots of nice little honeybees. And the trouble is, at the time, I only had 3 training images for the Varroa mite. And these were images I had found myself in my beehive. And that was not enough to train any computer vision system to find Varroa mice. Now, the fact, which I realized very quickly, was I could give to anyone, including my mother-in-law, who was willing to sit there and look for Varroa mites. I could give verbal descriptions. And so the verbal description is the Varroa mite. It looks like one of the bee's eyes. So look at the bees, they have eyes. And so it looks like one of the eyes, but it is red and it's stuck to the body of a bee. And so now it's much easier to detect the Varroa mite. And so some of you may have already found it. And let me zoom in to show it to you. It's there. And so instead of having to work like crazy to collect about 1,000 training images with the Varroa mite, I gave you a very simple verbal description. And the verbal description is good enough to train all of you to detect without any doubts the varroa. There is no doubt that that's a varroa. It fits the description. It's not one of the eyes of the bees. It doesn't belong. So it must be the varroa. And so with this training, you're able to do it. And so why are we not able to do it with our algorithms? Now, indeed, when you think of how humans communicate to each other about how to identify, for example, a species, they do communicate through a mixture of drawings, words, descriptions, sometimes details, and so on. And so here you see a picture produced by the Louisiana Department of Wildlife to help people identify the ivory bill woodpecker, which is the one on the left, and distinguish it, so in the top left, and distinguish it from other woodpeckers that might look similar, and also from ducks. And so this is it good enough to train people. And as you can see, there are names about body parts, attributes, and so on. And so indeed, the hope would be that we can solve any classification or visual recognition problem instead of just using the usual paradigm that we're used to, in which we have supervised training or unsupervised with some data set. Well, the expert also can provide some additional information, which is specified in natural language, drawings, equations, pointing, whatever it is. And it's much more data efficient than just a regular training set. So that's the idea. And as a benefit, if this works, since the specifications are done in human language, you would expect that once you've trained the AI system, that at inference time, it can communicate back to us in the same way. And so we are better able to understand what it's thinking and why it made a certain decision. So to summarize, I think that the goals for this community that is coming together thanks to the workshop organizers are that you want to learn from experts. And I would say this is something that is underappreciated, how difficult it is, because the experts typically are very few in any given field, and they are not they don't have infinite time to help us develop our system, so they want to spend as little time as possible. And so it should be, I call it lean training, namely use as few bytes as possible and as little time from the experts as possible. And then as a third goal, which is a sub-goal, is that you want the inference to be interpretable. So you want that the algorithm that you build at the time when it makes a decision, it's able to explain in the same terms as the expert used, learns the same language and is able to use it to describe what it's done. And then we can be more sure about its job. And so the previous speaker from Jason Corso's group was talking about level of confidence and the fact that it's not really very reliable. And this is something that all of us have experienced. Now, if you wish to have a model talk the same language of experts, I think it's inevitable that we develop a dictionary of parts and attributes. And so here you see again a diorama that helps us distinguish between an ivory-billed woodpecker and a pileated woodpecker, which is similar. And as you can see again, it makes it has pointers, it has names for parts that we know about, and attributes like solid black versus white triangular patch on the back and all of that. So this seems to be, to me at least, seems to be the way to go. And so we have to think whether we can train our models to, as they are being trained, maybe in a supervised way initially, to develop a language that can be brought back to the language we use in our job. So something I've been curious about is whether our models, which we train in a painful way using supervised learning, and it's fine for a few species of birds, are able to develop a dictionary of parts and attributes in an implicit way that can help them recognize new species with less effort. So what you have to consider is that when you think about bird recognition, you talk to a birder, somebody who is fairly proficient at recognizing birds, in order to train them to recognize a new species, you just talk to them and you say, well, it has, as you see in this picture, it has a red head and the back is solid black or whatever. And that's good enough, right? So they can go off and recognize this new species. Now, the question is, would our algorithms, once they've seen enough species of birds with a lot of examples, are they developing an internal language that allows them to learn new species in a very efficient way? And if so, then we should be able to develop techniques to make them speak and tell us about the different parts and attributes they see, and use that in order to train them from expert knowledge. And so the answer is no, our current models don't do it. And so this is a set of experiments I've done these last few months with some undergrads here at Caltech, which was part of our training. And so here you have a piece of the iNaturalist dataset, iNaturalist 2018, which you guys can download. And we took the insects part. And as you can see, the number of images per species, that's a vertical axis, is distributed as a long tail distribution. And so after species number 10, which you see on the left, the number of images per species drops dramatically. And so by the time you're at species number 100, you only have about 100 images per species. And as you reach species number 400, then you're down to 20 or 30 images per species, and that's not good enough. And so the majority of the species are out on the white zone on the right-hand side. You go from 400 to 2,000, and those have fewer than 20 or 30 training images. Now, we call the head the set of species for which we have lots of training examples, above 400, and we call the tail the set of species for which we have fewer than 300 training examples, and going down to 30. Okay, so the blue is the head, and so it is the few species for which we have tons of training data, and the green is the tail, for which we have very few training data. And so we'll try to see if by training on the head, which has lots of examples, the model can learn representations that are useful to learn more efficiently the tail examples. Now, what I want to emphasize is if you look at this appearance of head insects and tail insects, you don't see many differences. And so here on the left, you have species belonging to the head, on the right, species belonging to the tail, and there is no reason to believe that there are systematic differences in the appearance of these species. So what you learn from species on the left, namely that they have eyes and legs and bodies and so on, should be useful on the right. Now, if you do this and you look at what happens, you see that there is no benefit when you want to do well on tail species, no benefit in training on lots of head examples. And so let me explain how to read this plot. On the y-axis, you have an error rate in classifying the tail species, and you see that on the top you have 10 to the 0, namely 100%, and the bottom is 30% of the y-axis. And the number of tail training examples is along the x-axis, going from 1 to 10. And unsurprisingly, our error rate goes from about 100% or 90% down to about 40%. And so we see that indeed adding training examples to the tail species helps. However, all of those curves refer to different runs of the same experiment, while the model was being trained simultaneously with different numbers of head images. And so you see that having more head images doesn't help at all. Okay, in fact, it does hurt a little bit. So it's clear that our models, and this is Hera, which is the model, the transformer from Berkeley from a couple of years ago, very simple, works very well, and it's pre-trained on ImageNet, but we see that it doesn't help. And here we have more experiments. And so on the left, you have ResNet, which is the same story, and it doesn't, it works even less well than the transformer, than Hera. And on the top two plots, you have iNaturalist insects. On the bottom, you have Chinese characters, and the story is identical. Now, there is another story here, which shows you that pre-training on ImageNet has a big effect. And so the two curves that drop are when you train these models on ImageNet, and you drop down to 40% error. If you don't pre-train on ImageNet, you don't even have that benefit. So it's not that these models are unable to learn from other categories. Simply, they don't draw useful information about the specifics of the task, namely the type of species that you're going to recognize later. So we need to invent methods for combining language and images in better ways. And we need to find algorithms that are able to abstract away parts and attributes from classes of objects that we train. And so this is at the beginning of an example, and there are a few other in the literature, of course, and some we will see in this workshop. This is from Nihar Kondapaneni and Marcus Marx. It came out as CVPR 2024. And here they decided to use diffusions. And so the original image is on the top left, and you have a captioning system that tells you what is there in the original image. And this is a guess, of course. And then by using clip and cross attention, you can derive attention maps that are focused on each individual item in the picture, and using those as the input of some supervised classifier, you can do much better in semantic segmentation, object detection, and depth estimation. So it's clear that if we know how to milk information from diffusions or from VLMs, we should have some progress. I've not seen a study that tries to understand how much such information is there in a systematic way, and whether our hope of having a system that can be trained efficiently by an expert is well-founded or not. Okay, so our goal is to use efficient information coming from an expert in natural language drawings equations to be able to train an AI system. And the question is, is it going to work? And so here, just to conclude, I'm going to speculate if in this workshop, let's take the third or fourth edition in 2 or 3 years, are we going to see big progress? And I'm going to speculate the following. And so I'm also giving you a sense for what kind of experiments I would love to see people carry out to see if they are competitive in this world. So classification of species of plants and animals, birds, and so on, I would say yes. They have well-defined parts and attributes that are known to the experts. We should be able to see lots of progress in this. And of course, one of the challenges is pose invariance. And if our algorithms are able to detect the legs, the beak, the eye, the head, and also to classify their attributes, these invariances are going to be much easier than what we have now. So I think that here we should see lots of progress, learning a new species of birds from a verbal description in the next few years. Now, what about the problem of detecting the Varroa mite? And again, I'm quite optimistic that this should be doable for the same reasons that it can be described well. Now, here is some place where I want to inject a word of caution. So here I showed this picture of my motorcycle to ChatGPT, and I asked it, where is the fuel tap? And it says in the image, the fuel tap, also known as fuel petcock, is not directly visible, but typically on a BMW R75/5 motorcycle, it is located on the left side of fuel tank. Now, it turns out that it's very visible, it's there. And so here you have one of those delusional situations in which the VLM, or in this case, it's GPT, has read the manual of the motorcycle, and it's able to tell you back, and it's read the model of a motorcycle from the writing on it, but it's unable to process the visual information. And so this is a disappointing type of failure where image and text models use too much the text side and don't see anything. And so another question is, where is the oil dipstick? And again, it says it's located on the right-hand side, which is not even true, but it's very visible, it's there. So this, I think, is a challenging problem. I would love to see people work on this kind of problems and see if we can locate or detect complicated objects in mechanical parts and anatomy and the like. Okay, here is another challenge, which I think is going to be difficult. And so here you have a Chinese script from the 1600s. Maybe somebody in the room can read it, but not many Chinese people can read the script because it's old and you need to be trained to read it. And so here I'm wondering what kind of parts and attributes somebody could describe to help people who may be able to read modern Chinese. How do you train them to read old Chinese? So it seems to me that this kind of tasks, even in humans, relies on people spending a lot of time learning it by doing it. And so here I'm less optimistic. I don't think we will see much progress. And here is another one. So this is breast cancer screening. And again, my sense from talking to radiologists is that they don't have a good way of verbalizing what they see, and they have to train a lot. They have to see 10,000 studies every year to be at the top of their game. And so even for humans, the communication of the knowledge is mostly by practice and not by communicating with words. And so that's something I'm less optimistic. And here is maybe another one where, so there's a paper by D. Ara Bryant, where she was pointing out that the facial expressions is a multidimensional signal. Here there are two attributes, angry and happy. You will see more in a moment. And also for each one of these faces, she collected a bunch of responses from people over the internet of whether they thought that attribute was there. So you see the top left face, many votes for high score for happy, and many votes for low scores for angry. But as she points out, there are some of these attributes like surprise and sadness in these pictures, which are absolutely difficult to agree upon. And so you see that on surprise, some annotators say 0 surprise and some say very high surprise. And here on surprise and sadness on the right face, there is also lots of ambiguity. And so here again, if there is no consensus amongst humans, difficult to communicate with an algorithm on what to do, right? And so I suspect that also the nature of the stimulus is such that we need to train algorithms by seeing a lot of examples, and there is little we can do. Okay, so just to close, I think this is a great topic, and it will be very impactful if we can train more quickly our computer vision systems for new categories. And I expect progress in some, but not all the possible challenges that we want to tackle. And so I'm looking forward to this workshop to be held regularly every year and to see progress here. Thank you.
Yeah, thank you, Professor Pietro. That's a very nice talk. We have some time for a few questions. Anyone has a question, please come over to the stage so that he can see you. Yeah. Yeah.
Hello, sir. Thank you for a very wonderful talk. I'm very interested in this whole concept of auto-annotation. I'm wondering because our lab, we are using different types of paint and colored markings in order to preserve identity of birds that we're tracking. So in our case, we already know what species we want. It's a certain annotation, but it would be nice if, for example, we wanted to preserve identity and we would be able to say this is a bird, a white bird, but with blue markings, or a white bird with red markings. How feasible do you think that's you reckon that is, given everything that you've worked with and your lab has worked with? Thank you.
Yeah, so I don't know, didn't understand exactly the challenge. So you have video in which you're tracking some birds, and then you want to say, you want to type in the attributes, and you would like to use the attributes to be able to improve tracking. Is that what you're saying?
In this case, the end goal would be the tracking, if that makes any sense, but just in order to preserve the identity, right?
Yeah, no, I mean, you're absolutely right that if a system is able to parse out the parts and attributes of some object, it should be able to preserve identity much better. Now, if you look at the work of some ecologists that I know, and you can look at papers by Sarah Beatty, that there are a couple of surveys she put out. There is a lot of work on even animal identity. And so you would, if you're looking for grizzly bears or lions, you would like to know that the same identical individual is showing up. And right now, it's a bit disappointing because all that work is going on. It's very ad hoc. So for zebras, you know that you have to use the stripes. For whales, you have to look at damage to the dorsal fin or to the tail fin. For elephants, you look at little cuts in the edges of the ears. And so the vision expert has to know all of these tricks to be able to do it. And of course, we would like our algorithms to discover what is the information and use it. And so that's exactly as you say, it's something we need to do. Yeah. So anyway, I hope that it's going to be doable. I think it's going to be doable. If it, it's pretty obvious that if a human can do it from a description, then why not a machine? You would expect a machine to be able to do it too. Yeah.
Yeah, absolutely.
Thank you for the question.
Any other questions? All right, let's thank Professor Pietro Parona for the great talk. Thank you for your time.
Enjoy your
Hope to see
conference.
you next time in person. Yeah.
Yeah. Enjoy the conference. Bye-bye.
Thank you. Bye.
Thank you.
All right, hopefully it's all.
Yep.
There's an echo though. You turn it up. Okay. All right. Sorry about the technical difficulties and thanks for having me at the workshop. So today I'm going to talk a little bit about how do you get from annotations to measurements. And a lot of it is motivated by the fact that in many scientific and real world applications, the goal isn't to label something, but to measure something with certain level of precision. So for example, in some of the work we've been looking at, we want to measure like how many animals there are in a particular area. So you might want to conduct a survey from aerial photography, or you might be interested in disaster planning. So Red Cross might want to know after a hurricane, how many damaged buildings there are in a city. And in some of the work I've worked on bird migration, we'd like to estimate what is the rate of bird migration traffic over weather radars. So in each of these applications, there's a goal to count how many things are happening in a large set of images. And often these sets of images that you want to compute this data set from is very large, and you may want to rely on computer vision models to automate some of this because manual annotation is just very expensive. The challenge, of course, is current AI models, as good as they are, they're far from perfect. So on particular tasks, the model may not be accurate. So the problem might just be hard. We looked at some example of species recognition, where the current image classifiers, even state-of-the-art models, are maybe not able to recognize all these fine-grained categories. So a scientist might take a model like that. They might think the model works well as advertised in the test sets, but then they deploy it on a domain that they want to estimate, and they do not know a priori if the model is going to work. So your damaged building detector might work in North America, but then you deploy it in Asia. Its error characteristics are unknown. And another problem more and more these days is there are many, many foundation models to choose from, right? So how do I know which one to use and what to deploy in a new task? So often what happens is a scientist goes and auto-labels a data set, takes the data, it performs a count, like how many damaged buildings there are, and it gets they get a number. They don't know how to trust it or what even the error rates might look like. Okay, and they're stuck, and they often find that it's not good enough, and they throw at the result. Like if you're trying to write a science paper and all your labels are derived from an AI model, you'll get very skeptical reviewers. So a lot of what I've been thinking about these days is how do you bridge this gap? Like how do you get scientists who know how to run AI models, but may not have the expertise to develop new AI models or even improve them to a very high accuracy? How do you bridge this gap to get them to a setting where they can measure these quantities of interest, counts of things, and also get a sense of error bars around them? And the idea is that they could start labeling parts of the data set, and your algorithm should produce, through the use of AI and human experts, a measurement with error bars, and they can stop labeling and doing this annotation as soon as they think that the error bars are small enough. And that's a good thing to have, because each of these applications might have very different precision requirements. So Red Cross might be okay with a 10% error in damaged buildings, but if you're trying to study phenology or population decline, and the declines are in 1%, your error bar, the requirements for these scientific measurements are much higher. So how do we sort of get to a system where you can produce unbiased estimates with error bars and make use of the best AI models and human experts? So just to take a step back, let me tell you about some of the problems that I've been thinking about in this space and how we got to this way of thinking about these problems. And a lot of it is motivated by some of the work we've been doing on looking at weather radars to study bird migration. So if you haven't seen something like this before, this is sort of all the data that's coming in from the US Weather Radar Network over multiple days in April. Okay, so each of these dots is a weather radar station. The US has about 140 of them. There's one near Denver. And every about 10 minutes, you get a snapshot of what's in the atmosphere through these weather radars. So this network has been going on for about 30 years now, and the data has been systematically collected. And these weather radars are sensitive enough that they not only detect weather, but they're also tracking whatever is moving in the air, including nocturnal bird migration. So billions of birds migrate throughout the US every year, and it's all happening in darkness, and you can't really see them. But what you're seeing in each of these blips that are happening is every evening, birds are taking off, they're flying a certain distance, and these blips are getting larger and larger and more intense as you go to May. This is the spring migration happening. Birds are coming from warmer climates from the south, coming to the US and going up further north to Canada and Alaska. And because of the radar geometry, it's easier to detect the birds near the radar station. Okay, so, and the weather radars are not only just detecting bird migration, they also see other phenomena, like these are aerial insectivores called tree swallows. They get together and roost in very large numbers. Some of these could have hundreds of thousands of birds. And every morning, just around sunrise, they take off and they go up in the atmosphere. So you see these little blips. You can see insects, you can see bats. There are all these cool phenomena you can detect in weather radars. So about 10 years ago, a group of us got together. These are computer vision researchers, ecologists, birders, and the goal was, wouldn't it be cool to take, analyze all of the weather data archive that we have in the US and build algorithms that can extract all this information and understand and uncover like what is happening in the atmosphere, how does bird migration change over the years. Okay, so this was fun, and we built lots of cool computer vision algorithms to do this. So one of them is called MistNet. It's basically removing weather from the weather radar. So weather, if you're a weather prediction model, you don't care about bird migration, but because this is happening at very different intensities. These are the reflectivity in log scale. But if you're trying to measure birds, small amounts of precipitation coming in can make a huge error in your estimation. And also build models for detection and tracking of these roosts, and they work reasonably well. But and some of this led to cool science. One of the things that we found is over every decade, the bird migration is shifting by a day and a half. So the phenology is shifting. The same thing about roosting birds across. So ran this detector around 20 years of data around the Great Lakes region, looking at a huge number of scans, and found that the roosting phenology is also shifting. I wanted to stare at these figures because often the science outcomes, there's all these things that are happening, detection, tracking, but in the end, the figure that this is the measurement problem that they care about, right? So this is looking at the median passage state across different latitudes. And these are, each of these plots depend on huge amounts of detection and tracking and vetting. But the end result is something like, what is the median passage state on average across each decade? So that's the measurement problem we would like, and we would like error bars or confidence intervals around these quantities. We get the same thing about roosting phenology. In the first case, we're looking at overall migration. We could build AI models that were pretty good, just as good as humans for removing rain from bird migration. But the roosting models weren't good enough, right? So we, despite our best efforts, the best detector tracking method we could train only had about 50% accuracy MAP, which is pretty good, but that's not good enough to get these very, very precise trends that you're trying to track, okay? So what you actually have to then go to is, you have to work with graduate students to build labeling interfaces. And often a lot of science happens like this. You look at the outputs or even just labeling interfaces where you might start to vet these detector outputs. So we had to build a user interface where you could quickly go over these scans, and it took about a second to verify the scans per radar. And but it's a lot of scans. So 12 radar station, 20 years, there's about 600,000 scans, and it took about 183 hours to do it. If you had to go label it manually, this would be another order of magnitude longer. So the AI model did help the detection, labeling more efficient, but no, if I said let's now do it over 140 radar stations, the students were happy to not do it. They've all since graduated. This is something they never want to do. Okay. So what are the main lessons from some of these science questions? Like often scientists want to measure something on a large data set, but AI is not often good enough. What they really want from these models are not just predictions, but measurements with unbiased results, uncertainty quantification, and ideally expertise in these labels could be as few as possible. And as we saw from Pietro's talk, it's often difficult to get models to do much, much better. Like it took a lot of effort to go from 48% to 56%. There'll be multiple CVPR papers, but that doesn't really solve the measurement problem. You'd have to get 100 times more label to get the error rates to go by a factor of 10 or something, right? So, and often scientists don't have the time or expertise to improve AI model development. Okay, but the main takeaway is often the goal isn't to get every image labeled as accurately as possible, but the goal might be a quantity that you want to measure, like how many birds or what is the phenology or something like that. And the goal might be some aggregate quantity like this with a certain level of precision. Okay, so what I want you to think about is take a step back. Let's say you're a scientist, you're trying to solve a counting task or measurement problem. What is the best use of your effort to solve this, right? You could label everything, and sometimes that's actually the best thing to do because it gives you confidence in what you measure. It's a good teaching experience sometimes to the students because you label and you understand the data, which is not to be ignored. And works well for medium-sized problems, but doesn't really scale, right? So the current scientific frontiers, we're trying to look at data from huge amounts of images and so on, okay? You could invest in AI, which could be a good thing to do. It requires expertise, but more and more today with VLMs, it's possible to deploy AI models for a particular task with relatively easy through language, through a few examples. You might be able to get an AI model that works reasonably well. Does require some expertise if you do want to improve it further. Computation is a big challenge, right? So that's not always available. And it may not pan out for hard problems. You might be able to get a detector that works 50% of the time, but to get it to 99.9% is a huge amount of effort, right? So, and then even when you know the model works well, you may not be sure if it's going to work well in a new deployment scenario. Okay. So what I've been trying to think about lately is this idea that let's try to solve the measurement task directly and think of all the things that go into the process of getting to the measurement task within the framework. So things like active learning, what's the best use of labeling to improve the model? If you have multiple models to pick from, which one should you use? And last bit I'll talk about a little bit is this idea of directly estimating the quantity through a statistical approach, okay? And so a lot of this work kind of fits into literature from statistical sampling, like survey sampling, but also things like active testing, prediction-powered inference, and covariate-based counting, and so on. Okay, so try to summarize this in a little bit. Okay, just to make this a little bit more concrete, try to guess the number of birds that are in this image, right? So any guesses? Yeah, 1,000, okay? 10,000. Okay, so this actually is an image from one of these roosts. So we went down to the old line, Connecticut, where these roosts are. And the idea was, let's take pictures of these birds flying out of these roosts so they can calibrate the radar. with actual ground truth. Okay, but it turns out we took hundreds of these images and nobody actually wanted to count them. So these have been sitting around in our hard drives for almost 10 years. And just to show you how many of these birds, these are tree swallows in each of these images, as many of these birds. Okay, so how might you want to do this with AI? Maybe you label a few images, have a bird detector, and you run the bird detector on all of these little tiles, and you get a number. Okay, how good is it? So you might look at some of these detections and maybe see, okay, maybe the detector isn't doing so well, it's missing, maybe this is an underestimate. So it'll take a bit of time, more vetting to get a sense of this. Okay, so the current estimate you wouldn't know how to use without sort of more work and so on. Okay. Another way you can get an estimate is just through sampling, Monte Carlo sampling. So you could go, so there's a little bit of math. This is just saying, I want to compute the total, which is the number of tiles times the average number of birds per tile. How do you get an average? I sample, let's say just a few tiles, count the birds in them, get a mean, and then multiply by the number of tiles. They'll give you an estimate, and you can get an estimate with as many tiles as you want to label. The estimate can also give you a sense of variance, right? So the variance estimate from the samples you get. And asymptotically, this will converge, Gaussian, all the good things. If you assume about the data, well, you can get a tight confidence interval around that mean. Okay, so this is Monte Carlo estimation. No AI involved. This is things you can do with just labeling a fraction. Okay. So that gets to this idea of how can you combine AI model predictions with humans through this idea of importance sampling. Okay. So Monte Carlo sampling, uniform sampling can be bad. You might end up in the sky or the reeds part of the image. There weren't any birds. Your estimate could be very high variance. So instead of computing the expectation under uniform, you could sample this tile according to some proposal distribution Q and compute the mean, but you have to weigh the samples by this P over Q ratio because you're oversampling some tiles more than the others. Okay, so this is importance sampling. And as long as you have a proposal distribution that has some nice properties, this equation always holds. Okay, what you can also show is that if you want to compute the total, the best proposal distribution is to sample tiles proportional to the true count. Okay, that's going to give you an estimate that has zero variance. Of course, this is exactly what you're trying to estimate. You don't have access to the perfect proposal distribution. But you have an approximate proposal distribution as is coming from the detector. Okay, so this is now you could sample proportional to the detector counts. And as long as the detector counts are correlated with the true counts, you would expect for the same amount of labeling effort, number of tiles you label, your estimate will have a much smaller variance than the other. Okay, so this is something we proposed in the discount paper, detector-based importance sampling, where the idea is, suppose you have a building damage detector or bird count detector, and you want to get an unbiased estimate of the total count with some confidence intervals with as few labels as possible. You could sample proportional to the detector count. And some of the technical things we proposed there were, how do you solve multiple counting problems? Maybe you want to solve across, and also reducing the variance through control variance. So how does this look like in practice? So this is showing you the number of birds that flew over KGRB radar station across many days through this roost detector and counting. So this is the ground truth. If somebody went and drew boxes, you estimated the radar intensity around that, multiplied by some number to get the number of birds. This is what it would look like. This is what you get from a raw detector. It has false positives, and your estimate is quite a bit off. Okay, and you start doing this count. You label 15 different days. Your estimate looks like the yellow line here, and you also have error bars around it. If you're happy with this error bar, you could stop labeling, but if you start labeling more and more, the error bars will shrink and your estimate gets smaller and smaller. So this gives the end user a way to use a labeling effort to get to the desired level of precision. This is quite useful in practice for the user. Okay, so there's some experiments from the paper where we said, oh, we want to estimate number of damaged buildings. So this is actually deployed within the Red Cross, where they often are trying to run a building damage detector, but they know it's making mistakes. So how can they get to the right answer or get some confidence intervals around their estimates? Because they can ask humans to vet the outputs, but they also want to do it as quickly as possible. Okay, so this is the error, is the number of samples. Simple Monte Carlo is just label and get the counts. That's the blue line. It goes down, but much more slowly than discount. And then IS count is, instead of using detector proposals, use some other covariates. And so this was based on some prior work. But the other covariate could be, let's use the number of buildings as a proxy for sampling, or add average migration on average to pick which days you might want to label. Okay. So you get quite a bit of savings in labeling effort to get to the same level of error. And at all times, you still have an unbiased estimate. Okay, so this was discount. And more recently, we've been developing this framework a little bit more in this idea that we should think about all these frameworks to within this active measurement framework, where as you get to label more data, you might want to also use these labels to fine-tune your detector, right? So this is idea of adaptive importance sampling. And the idea is your detector might benefit a lot early on from new label samples in the target domain. So if you can improve the proposal distribution, you would benefit a lot at the start. And then there's a technical issue, which is when you're labeling something, you want to sample without replacement. So the tiles that you have labeled should not be sampled again, which in the previous Monte Carlo estimation, you're sampling IID with replacements, you get to see the same quantity again and again. And this makes a difference later in the sample, because as you label all the tiles, your error goes to 0. It's because you're sampling on a finite data set. Okay. And we also derived some estimators that worked well, and confidence intervals in the scheme. Okay, so how does active measurement work? So the idea of active measurement is at time t, you have labeled t of these tiles. So the estimate of your total is the things that you've already labeled and an estimate of the remaining. Okay, so you're sampling one from something you haven't seen, and this is f over g is your important sampling correction. Okay, and you can combine your estimates over time. And if you're careful about how to combine these estimates later in the time are more accurate. So the weights are not uniform, but they add up to 1. You can derive an overall estimate in any given time. Okay, and then as you label, you can also fine-tune these detector. The proposals at over time 1 to t need not be the same. The Q can be time dependent as well. Okay. So how does this look like in practice? So these are some of the data sets. We unfortunately had to label to get the ground truth answer, but then once you label it, you can run experiments and do this. Okay. So again, so looking at error as a fraction of labeled tiles. That's the sky image. So blue is the Monte Carlo estimation. And then the raw detector, as you fine-tune the model over time, you look at the prediction error, and the prediction error sometimes doesn't go to 0. Sometimes the error goes down, and as you know, with model fine-tuning, sometimes you'll end up with a sample that changes the bias, and then the estimates could change quite a bit because these models aren't perfectly calibrated. But as you fine-tune them, you use their predictions as new proposal distributions for the remaining tiles. Okay, this is Monte Carlo. It goes down. this is important sampling if you use the detector counts. And this is the effect of model fine-tuning. So as soon as you see about 10 or 20 new samples, the predictions from the fine-tuned model tends to be a better proposal, even though it doesn't necessarily improve the prediction. You see that divergence. And then sampling without replacement helps you towards the end. Okay. So if you're wondering how many birds there are, this is the right answer. It's about 12,000 birds. So 10,000 is a pretty good guess. Okay. How does the model look like? So at t equals 0, the model's predictions were around 7,500. And then as you start to label a few of these styles, your estimates start to change, and the error bars are starting to shrink. Okay, so after just labeling 50 tiles, you have an estimate which is close to the mean, and the error bars are shrinking. Okay. And maybe that's good enough. So 50 tiles isn't as bad. There are 1,400 total tiles, so 50 is about 1/10 of the labeled data. And you may want, if you want even tighter estimates, you would have to label even more. Okay, so that's the NeurIPS active measurement paper. And lately we've been thinking about many extensions of these. One of this is this idea of multiple target estimation. So if you want to count not just birds, but also, let's say, the number of trees there are, or in this task, you have a semantic segmentation task over many species of coral reefs, and you want to know how many pixels across your data set does each of these species occupy, to get some sort of population estimate. You might have a segmentation model that gives you predicted counts, and you have humans that can label. What's a way to best combine them? The tricky bit here is that, as you saw, important sampling tries to pick images where the counts are higher for a species. But when you have multiple targets, these could be conflicting. The support for images for one category might not be the same as another. So some of these estimators don't work very well. So this paper did an extensive evaluation of all these estimators that exist from the survey sampling literature, things like uniform sampling with difference estimators you can think of as control variates, or important sampling where you do a round robin type thing where you sample one, then another class, and so on, or a mixture of samples and these subset sampling based estimators, and analyze the performance as a function of the quality of the model, the number of classes, and had some useful recommendations in practice. Okay, and all of these methods tend to vastly reduce the number of samples you need to label to get to unbiased estimates, and have much smaller confidence intervals compared to just labeling alone. And using the AI models themselves, you don't get confidence intervals or any guarantees on your measurement. Okay, another was work with Justin, with Sarah, who is also a co-organizer, is about model selection. So let's say you have many of these models to choose from, and nowadays you can go to Hugging Face and download hundreds of models that could be relevant for your task. Which one should you use? Often you want to know, to get the estimate of which one works best, you would have to label some data. And this paper tries to ask the question, what's the best way to pick the best model with the fewest labels possible? Okay. So in this work, the model developed a Bayesian framework where the idea is you have all these models, you have your entire unlabeled data set, which is a huge advantage. You want to know the performance on this specific data set. So you could look at the consensus of models' predictions, when they agree, when they disagree, and use that to guide sampling. Okay, so the way the model works is it starts with model predictions. It gets in a sense of what is the most likely label for each image, and what is the performance of each matrix or each model based on an estimate of its confusion matrix, and then goes and asks, which point should I label that can help me improve the posterior, most information gain over what's the best model possible. Okay, you label and you repeat this process, and these are some of the curves from the paper. So if you look at what fraction of benchmarks do you get, less than 1% of the best model possible as a function of number of labels queried. Random sampling is what you might do to build a simple data set to label. But if you do something like CODA, you get much better performance compared to a bunch of other active measurement schemes. The reason it does very well is it's using the entire unlabeled data and the model predictions to do a joint analysis. Okay. All right. So a lot of what I described so far has been thinking about model selection, active learning, uncertainty sampling, statistical estimation in isolation. But I feel like when the end goal is the measurement task, there's an opportunity to think about a framework which tries to figure out what's the best state in which you're in. Are you at a place where reduction in error would come mostly from improving the model? Or are you at this place where you're at diminishing returns and you should stop improving the model and just reduce the Monte Carlo error through sampling? Okay. And we don't quite have that. And I'm pretty excited to think about what would be this ultimate AutoML or labeling interface where you could make these decisions as part of your learning process and decide, labeling, improving the model versus sort of just reducing the error through vetting the model outputs. And I think this is where a lot of interesting research could come in, where you want to allocate human effort and AI effort to give you the best value of information. So this is also things that people in the statistic community have thought about a lot, like experimental design and so on. But it gets quite tricky because these aren't like coding experiments or something where the value is immediately computable. So some of this require model training. They're expensive. Model evaluation is expensive. And you could run AI agents with different complexities. So there's cost associated with inference and training, which we don't have good handles for. But I think it's a good problem space to work on because it combines all these aspects of sampling, expert-guided annotations, thinking about domain shift, and all these aspects of the problem within this framework of solving a measurement problem directly. Okay. So with that, I'll just stop here and happy to take questions.
Any questions, please?
Yeah.
Yeah, please.
I think you just yell, people can hear you. Yeah.
Thank you for a very comprehensive talk. I was wondering, for these, for the bird detector ones, were they all on a relatively clear background? And if so, could this be adapted to a method where maybe the background wasn't as uniform? Would it still hold? Okay, you reckon it would.
Well, so I think the images I showed you, I'm sorry, I don't know what happened. The reeds and birds are just prototypical examples, but in the paper, we've done lots of experiments with weather radars and building damage detection. These are, think of this as standard object detection counting tasks where you might have detectors, but they're not perfect. So as long as the the counts are correlated with the ground truth, you tend to benefit from these proposal distributions. But yeah, if it's completely wrong, then you wouldn't do so well.
And thank you. And then maybe a follow-up question. Were these just static images, or were they also cross videos as well?
Yeah, the radar ones are videos. So to go over them very quickly, but essentially you detect and track these things that are many radar scans over days. And then from this track, you get a count estimate. So it's a much more complex thing for weather radars, but for the bird counting and building damage, they are just images.
Any other questions?
I have a quick question. Thank you very much for the great talk. So you mentioned about like model selection and like for example, all these different things. I'm just wondering for like real species like recognition or detection, well, you only have a few label data. Like,
Right.
I'm just wondering what's your take on the importance of validation data when you are training the model or selecting the models?
Right.
Does that impact the performance a lot, or do we actually need a validation set, or how do we do validation?
Yeah.
Yes.
Yeah, I mean, believe it or not, when you're starting a new problem, you don't have a validation set, right? So constructing the validation set is part of the challenge in many of these scientific questions. So I think that, you know, if you don't build a good validation set, your estimate of performance could be very off. You could get, you know, very, very different model selection choices. So the active model selection paper was trying to say, what's the best way to create a good validation set to pick the best model? But I think like that's a good question in the active measurement framework, because the samples you select to get good estimates for measurement of model performance may be very different than the ones that give you the best improvement in training performance, right? So the samples for active learning might be different from active testing, from active directly measurement. So the sampling strategies could change. And there's probably a room for some meta algorithm that says, oh, maybe you're in this active learning phase. Now you're in the active testing phase, and now you're in the active measurement phase. And how do you know where you are is sort of the classic RL kind of problem in exploration, exploitation. And we could probably take some things from there.
Yeah, great. Yeah, thank you very much. Let's thank Professor Majuli.
Yeah.
Thank you.
Yeah. Yeah, sorry. Do I need to take
Sorry, I forgot to mute. Okay. Yeah. So for the next 20 minutes, I will give a brief sharing about the lessons and insights we learned from the different competitions. And at the end of this talk, we will have the top one team from the Auto 3D challenging to give us a brief presentation of the methods in terms of how they achieve the top score. Okay. This workshop was organized by like many people. My name is Tian, Hannah, and Yechi, and Tong, and Shu. They all contribute a lot of efforts in making this workshop happen. Unfortunately, due to the visa, they were not able to be here, so I'm just on behalf of all the team. Okay. To begin with, I would like to just briefly recap the motivation of our workshop. As Shu has already mentioned, like earlier on, our setup is that in the typical data annotation setup, the domain expert designs the data annotation instructions, which contains some visual examples, some text descriptions, and then they use this instruction data, send it to the human annotator for label massive data, and then they want to use the label data for training an X model to facilitate a downstream task, right? And we all know there are a lot of different tools or softwares like Scale AI or Voxel 51 that develop different pipelines or tools to help you speed up the data annotation efficiency or performance. But however, there's also like foundation models like Grounding Dino that can directly predict the bounding box for you, right? But as Shu mentioned that these foundation models, they have some bias or misalignment between their pre-trained knowledge with the expert model. So for example, in the lab example, the bicycle, when labeling a person, when labeling a bicycle object, the new things, instruction actually want to group the rider with the bicycle, but the foundation model actually separate the person with the bicycle. And in another example, the trailer, the new things want to label only the head of the car and separate the trailer from the head trucks. But the foundation models like Grounding Dino, they capture them as all. And so there's a misalignment. So we need to be cautious when we adopt the foundation models. And in addition to sending hiring the human annotator, another in some natural science domains like ecology, like people deploy the underwater cameras to capture different fish, like long videos of different type of fish to understand trying to understand the biodiversity. They actually require experts themselves to group together and to manually annotate these captured video data. And this is actually very label intensive. And some other examples like the birds, people also use the cameras mounted in the wild trap to record the videos of birds and then trying to recognize the different birds. And so as I just mentioned, this procedure is label intensive and it's tedious and it's very costly because it requires the experts' efforts. And the annotations itself, they can be erroneous, subjective, and biased, and inconsistent. And that is because you have different human annotators, right? So you have this kind of inconsistency. So to solve these issues, we wonder, can we actually develop methods to automatically annotate domain data with domain expert crafted data annotation guidelines to help us train a model that can replace these experts, replace these human annotators to produce reliable predictions. So that is the motivation of our AutoExpert workshop. And we crafted two challenges. The first one is the ASA, automated species annotation for ecological research. And the second one is Auto3D, which is automated 3D annotation for autonomous driving. And for the next, I will first share the results from the ASA, the species recognition. So for this challenge, we have a total about 9 data sets that covers from the semi-aves, like the birds, fungi, or some like rare species, some insects, some weeds, mollusca, and some other insects. And also we have some plankton. Well, you can only see them in the microscopic. And we have these different plants. So in these data sets, we want to test the model to recognize the species level, and we provide the data in a 16-shot setting. And besides the visual images, we also provide the attention guideline, which consists of the text descriptions of different species. And the metrics for this challenge is just the marker average accuracy for each benchmark. To encourage the competition, of course we want to submit a baseline, and we want to encourage other people to compete with us. We want them to outperform us, right? And our simple baseline is a feature fine-tuning from a CVPR'25 paper. And in these methods, we just simply grab a pre-trained visual encoder, for example, the OpenClay VITB32 model, and then we put a classifier on top of it, and we just simply do a full fine-tuning using the few-shot data. And if you are interested in this method, so you can look at for the bottom for this paper. And and here is the overview of the challenge results. So in total, we have about 8 submissions besides our baseline methods. And as you see in the ranking, the blue box, the green box is our simple baseline that do fine-tuning, full fine-tuning. And the top one team here actually on average improves the baseline by 25% average accuracy, right? That's pretty amazing. So in the next, we will share the insights we learned from the methods and discuss some future work. So the first insight we would like to talk about is that usually when people do future learning, they grab a pre-trained foundation model, either like OpenClip or ImageNet pre-trained models, and they have limited data, so they always I think in the trendy future learning, people do parameter efficient fine-tuning, which means that they freeze the backbone of the pre-trained model to preserve the pre-trained knowledge, and then they learn some small number of parameters with the frozen backbone. For example, the prompt tuning, or they just do some learn some learnable prompts, text prompts, and also you can learn some visual prompts as well. And also they can do adapter learning, like LoRa or Clip adapter. The key idea is to learn additional components, but preserve the frozen pre-trained backbones. And in contrast, as I just mentioned, we have this simple full fine-tuning baseline, right? So how which way should we take? How do they perform compared with each other, right? So the first insights we have from the results is that we find that simple full fine-tuning actually outperforms parameter efficient fine-tuning. So here, this plot shows the accuracy of each data set using different fine-tuning methods. So the green bar is the full fine-tuning, the gray bar is the VPT, which is like the visual prompt tuning, and the yellow bar is the LoRa, which is kind of while we're using the fine-tuning large foundation models, right? And if we look at the average accuracy, we see that the full fine-tuning actually outperforms. And it is mostly true for most classes, for most data sets, except like Wiz or some Mollusca, but the advantages of full fine-tuning is obvious. And if we look at the ranking, these the submission 8 and 9 are actually the LoRa and the VPT methods, and our simple full fine-tuning baseline actually outperforms both of them. So our first insight is that we should use when we do future fine-tuning, we should not be afraid of full fine-tuning. And this is not only because it yields better performance, but also because we only have a few label data. So the training cost is not that significant, larger than the parameter efficient fine-tuning. So that is our first insight. The second insight is that when people do future learning, they grab different pre-trained foundation models. They can use OpenClip models pre-trained on line 400 million data. They can also use BioClip models pre-trained on tree of life 10 million data, right? So these are two different type of models. So when we apply them to this kind of species recognition task, what we find is that domain-specific pre-training outperforms general open world pre-training significantly. So as you see over here, the OpenClip, the future fine-tuned OpenClip model, the future fine-tuned BioClip model significantly outperforms the future fine-tuned OpenClip model, even though the pre-trained data is only 10 million in one case, while the other one is 400 million, right? So this just suggests that if you want to solve the species recognition, it's better to grab a model that's already pre-trained in species-related data. They should help in your downstream task. So that is our second insight. Our third insight, as Shu mentioned earlier, we want to embrace not only open world models, open world pre-trained models, but also open world data, because we have all this internet data that's available, publicly available. So some submissions, they actually try to retrieve open data and then add that to the limited training data and combine them together for training or fine-tuning a model for species recognition task. And here I'm just showing the idea in our CVPR'25 paper. to illustrate the idea, so basically for a specific downstream task, for example, like a birds, we have a few shot annotated task-specific data. These are like images and text descriptions, right? And we have these open world models like visual language models. And of course, we have, and at the same time, we have the pre-training data that's available to the public, like law enforcement data, right? So from this pre-training data, we can retrieve relevant open data that are relevant to the specific task. So for example, you can see these birds, you get this like sketches, like you have the birds printed on the clothes, you have these birds on the stamps. And you may notice that this data has like domain shift with your downstream data that are appearing in natural skies, natural backgrounds, right? So to leverage this retrieve data, we actually propose a two-stage training pipeline. Well, in the first stage, we just mix them together to train visual encoder and classifier together. And in the second stage, we just fine-tune the classifier again on the balanced few-shot annotated data such that the prediction will be balanced, and we can also mitigate the performance. If you are interested in more details, please look at this paper. And as a result, so again, the submission 7 is our baseline, simply full fine-tuning on few-shot data. And if we add more retrieve data, we can obtain submission 6, which is like about 2% accuracy improvements, right? But you may find this is not, the improvements is not that big, but it's worth noting that all these top 1, 2, 3, 4 submissions, they all use retrieve data. It's just like from different data sources we retrieve. For submission 6, we retrieve from line 400 million, but for the top ranking submissions, they are retrieved from like unnatural data sets from other like biological relevant data sets to fine-tune that model. And they achieve significant performance improvements. And also they use the retrieve data to mix with few-shot label data to fine-tune the bioclip model. So it's a combination of the domain-specific pre-trained foundation models with retrieved domain-specific data. And the issue here, you may wonder, is that there could be some data leakage, right? Because we are just retrieve data from the open world, and it may contain some test images in your benchmark, right? So we'll discuss this issue later. And in addition to retrieve data, the other insights is that we can also leverage large multimodal models like Queen, GPT-5, or Gemini to post hoc correct predictions from the fine-tuned expert model. And the idea of this is very simple. So initially you use a few shot label data to train the expert model. This expert model can be just like bioclip fine-tuned or OpenClip fine-tuned visual encoder. And this expert model will predict top K predictions. And then the way to leverage large multimodal is to feed the top K predictions along with the few shot images for the top K species and also the softmax probabilities. And we construct a multimodal prompt to prompt the LLM like Queen to ask it to re-rank the top K predictions. And our insights are like, basically, we find that the expert models, although sometimes they can predict ground top 1 prediction, but the actual ground truth is usually contained with the top K prediction. In this case, is in the top 3, right? And we want to recover the ground truth from the expert's prediction. And we use LMM to do re-ranking to trying to recover the ground truth answer. And after the re-ranking, we just pick the top 1 ranked answer or prediction as the ground truth. And this way we can recover. And surprisingly, as you see here, the top 5, the number 5 submission is the poke submission. And on average, it yields over like roughly 5% accuracy. And it's even more than when we retrieve more data. So it just provides a simple way that you can combine your few shot fine-tuned expert model with the large multi-models. Like you don't necessarily need to fine-tune the large multi-models. You just grab a GPT or grab Gemini to ask it to do a post hoc correction. And we find this is an effective way to improve your recognition accuracy. Okay, so now we talk about the limitations in the future work. So we do have to admit that our benchmarks, because we use publicly available data sets, and when people do retrieval from the internet, they unnecessarily they may retrieve the testing images. And there is a data leakage issue, and this is simply because we use public data sets. And in fact, one team actually hacked the leaderboard by retrieving the data from the original training set. So yeah, so it's an issue that we need to be cautious. And so in the future work, we do plan to leverage some private data. And this is because a lot of natural science research, they have abundant highly specialized data, but they do not put it publicly available. And this data, for example, like the paleontology shown over here, where you have to use some microscopic to see the detailed structures, and also some like phytolithology and some like ichthyology, like different the fish, the mouse, the shape of the mouse of different types of fish. These data are highly specialized and highly customized, and at this moment, we do not have access to this data, but we do plan to use such data in our future challenges. So, okay, that is our first challenge. Okay, now let me talk about the second challenge, Auto 3D, automated 3D annotation for autonomous driving. This challenge we built from the New Things dataset and Panda datasets, which released the authentic data annotation guidelines. And as shown in this example here, these guidelines, each class, they are demonstrated by few visual examples and some descriptions about how to label them, right? And the goal of this task is to annotate unlabeled or testing images in terms of both RGB and LiDAR with 3D cuboids for the target classes. And in terms of the challenge benchmark dataset, we annotate the Panda set with 3D cuboids as the final benchmark. But we also guide the participants to use the new things for research and methodology development. And we want to highlight that re-annotating the Panda set is actually necessary. And this is because of two aspects. The first aspect is shown on the left image, where you can see that the original Panda set contains a lot of bounding boxes that are entirely like invisible in the RGB images. So these bounding boxes, they does not like capture anything, but they are presented in the public data set. And this can be from the inconsistent annotation and the low quality human annotator, or the annotator, they could be just like detect something in the LiDAR map, but when they try to map them back to the RGB images, it's totally invisible. So to remove this issue, we actually need to re-annotate the data set to remove these like ghost objects. And now we have this data. And this is also advantage of this benchmarks, because now we have this re-annotated ground truth labels that no one else can access it, right? So when they do retrieval, they cannot retrieve this or annotated labels. So this also addresses the data leakage issue. And an overview of the annotated datasets, we annotate total 25 object categories spanning from different cars and different objects like corners or like barricades, something like that. And then we sample about like 200 non-continuous frames to ensure the diversity of the scenes. So the frames are now like continuous, so they capture different backgrounds, different scenes, different vehicles, those kind of things. And in total, we have more than 4,000 instances. And from the 200 annotated frames, we pick 8 for validation and 192 frames for testing. And in terms of evaluation protocol, in the training process, in the annotation guidelines, each class is demonstrated by 4 to 8 images and descriptions. And the images can be used as a federated training set, which means that each image is only annotated exclusively for the target class. So for example, here, this image is annotated for the truck, even though it has like barricade or other signs or other information, but we only annotate, we only provide the bounding box for the target class. And we do not provide the 3D cuboids for training. We only have the 2D bounding box for training. And in the testing, we want the model to predict the 3D cuboids that predicts aligned RGB frames with 2D bounding boxes, as well as the LiDAR sweeps. And in terms of metrics, because we are evaluating the model in terms of both 2D and 3D, so we have MAP 2D, MAP 3D, and also for evaluating the 3D cuboids, we have this revised nuisance detection scores. And here we do not contribute the average attribute error or mean velocity errors because we are not doing any motion planning stuff. We are just like doing pure detections task. So similarly, we also have our own baseline. This pipeline shows our two-stage framework. In the first stage, we have we have a foundation model, and we simply fine-tune these foundation models, which is a 2D detector, to predict the 2D bounding box in the RGB images. And in the second stage, we lift the 2D bounding box to a 3D cuboids through some like multiple hypothesis testing, and then we will introduce the details later. And if you are interested in our baseline methods, you can refer to this paper mentioned over here. Okay, now let's talk about the first stage, 2D detection. So in this stage, basically, what we find is that the category names that we use to prompt a foundation model or to fine-tune a foundation model is actually very important. So here, the first step we do is we obtain refined category names by prompting like GPT-4o. So given a text description and some like visual examples, these are from the data annotation guidelines. The first thing we do is we prompt, for example, ChatGPT to give us some descriptive terms related or relevant for the objects. So for example, for the police officer, some other synonyms or some other relevant words to describe them are like law enforcement officer or policeman, a policeman, or some traffic policeman, right? You can refer to the same concept using different words. And now we have these different descriptive terms, and we do a zero-shot evaluation to help us select what is the best way to refer to these concepts. And we do this by using zero-shot prompting grounding dyno model by selecting the different combinations of these descriptive terms by selecting the one that yields the highest precision. And once we have this optimal prompt, which is the best way to refer to the visual concepts, we use these concepts to fine-tune our foundation models, like grounding dyno for 2D detection. And one thing to note here is that in addition to obtain the synonyms or the other descriptive terms, we also ask the foundation model to give us some like spatial prior information, like the length or width or height for these visual concepts. For example, this policeman, the average height is about 175 meters, and this information is used in the second 3D cuboid prediction stage as the prior spatial information to help us improve the performance. And as a result, in the first stage, what we find is that when we simply replace the original class name with some refined class names we found, we can improve the grounding dyno performance significantly. And when we fine-tune the grounding dyno further with these refined names, it's actually further improve the performance. Yeah, so these are some summarization of our insights. The first insights we have is that we need to speak the same language as foundation models. And the idea is that we use some refined names or some other synonyms to refer to the original class names. So for example, there's one class called like temporary construction barriers. That is the original class names. And our refined name is the plastic pedestrian barricade. And we find that by simply prompting the model with these refined names, we can improve the detection performance. And this is probably because in the pre-training of these foundation models, they see the similar objects more frequently appear with these plastic things. So if you mention about plastic barricade, the model understands better in terms of detecting these visual concepts. And also when we find that fine-tuning the model helps with future visual examples helps. And if we fine-tune the model with these refined names, it performs the best. Okay, now we move on to the second stage, from 2D to 3D lifting. In this stage, we also utilize the help from foundation models or AI. So for example, here from this, these are the prior information we obtained from the first stage. And we feed the visual image to the ChatGPT. We ask it to output the dimension of these objects and some orientation that how the model sees the corresponding, like I think is a car. And then from this model's output, we combine the camera intrinsic parameters to obtain some initial predictions of the dimension and the orientation of the 3D cuboids in the 3D space. But this is not the final prediction. To obtain the final 3D cuboid prediction, we do this kind of multiple hypothesis testing, which is basically we are trying to rotate the 3D cuboid in the space such that it can maximize the LiDAR sweep, as well as when we project the 3D cuboids back into the 2D RGB images, it can have the highest IOU with the original 2D bounding boxes. So we do this kind of tweaking, rotating, and then select the best one as our final prediction. So that is our stage 2 3D cuboid generation. And as a result, our methods called Auto3D significantly improves the other previous baselines. And our insights here are that we should leverage the AI, and the AI actually helps us to obtain some prior information about the heads, the size of the objects, and also it can help us to adjust the orientation of this. And the second insights we have is that the domain expertise is also very important. We cannot just totally rely on AI to do all the things to predict the 3D cuboid. We also need the camera experts to obtain the initial dimension orientation based on the camera intrinsic parameters like the focal length, etc., etc. So we need to combine the both AI and the domain expert for solving this task. And here is my last slide. We look at the final challenge winner. So the second submission is our baseline methods. You can see it's already very powerful. And we have the top one team, iMerit, who achieved better performance. And that's all for my part. And next, I think we have some time for the top one winning team to show how they achieve the top one performance. Okay. Hi, Guanjun, are you there?
Yeah. Hey. So should I share my screen and present?
Sorry, we can't hear you. Hold on a second. Can you say again, please?
Hi, can you hear me?
Yes, we can.
Yeah.
Hold on a second. Yes, would you please share?
So, hi everyone, my name is I'm an engineer in iMerit, and I'll be presenting a submission for the auto annotation challenge. And our approach is very much similar to the baseline approach. So I'll just start with the overview. So this consists, so as explained the baseline, as the baseline approach was explained now, our approach is very similar. We have 3 stages. Stage 1 is 2D detection, but for 2D detection we are using SAM3 instead of grounding Dino. And stage 2 consists of 2D to 3D lifting, where we try to localize point cloud clusters belonging to the 2D segments detected by SAM3. And then in stage 3, we are trying to fit a cuboid to the point cloud cluster, very much similar to the baseline approach. So coming to stage 1, again, as following the baseline approach, we have used class name synonyms instead of class names directly to prompt the SAM3 model. And we observed that using class name synonyms instead of class names directly as prompts increases NDS score on the val set by like 4.2%. And apart from that, we have also used different score thresholds for each class to increase the overall 2D recall value. Further, we fine-tuned SAM3 with a low-rank adaptation method for 7 classes with low recall value. So, and that further increased NDS score by 5.1%. We also tried fine-tuning SAM on all the classes, but we observed that with that, we're not getting better NDS value on val set. And some classes regressed on the recall value. So we dropped that and we kept this fine-tuning to the 7 classes with low recall values. Coming to 2D to 3D lifting part. So in this part, we have to localize a point cloud cluster belonging to the 2D mask. For that, we project the whole point cloud in the 2D image and keep the points whose projection falls in the 2D mask. And after this step, we'll have multiple clusters at different depths. So we'll select the cluster. So here we are just using a heuristic. We assume for most of the categories, the nearest cluster is the object cluster, but for vehicle categories, the biggest cluster is the object cluster is our assumption. This assumption gives us better results on null set, so we keep this assumption. And there for car category, as it is the most frequent category in this data set, we have further sanity checks to ensure it is not going out of range for length, width, and height values. Like we are not having false positives like wall and other things as car category. So, and then stage 3 is cuboid fitting on this point cloud cluster. So again, similar to the baseline approach, we use multi-hypothesis testing where we generate multiple cuboid proposals with offsets in translation and orientation around the cluster centroid. And each of this proposal is scored on the basis of IOU of their projection with the 2D box, as well as the fraction of points inside the proposal, fraction of points in the cluster inside the proposal. And the best scoring cuboid is kept as the final box. So after doing all these things, we observe that orientation, we are still high in orientation error, since the baseline approaches uses VLMs to estimate yaw, like GPT-4o and all, and we are not using that. We see that we are still high at orientation error. So we try to use different approaches to reduce that orientation error. So what we have tried here is using 3D detector trained on Agover's 2, that is LAN model, and using that to refine yaw and extent values for the MHT fit cuboid. So what we do is, if LAN predicted cuboid and MHT fit cuboid are within the radius of 2 meters of each other and they belong to the same class category, we take the yaw and extent values from LAN model, but we keep the centroid position from the MHT and 2D to 3D lifting part. So this helps us in reducing the orientation error, but not significant enough to contribute to NDS, because it's after doing all this, although it reduces by 33%, but it's still above 1. like 1 radian, and then it does not contribute anything much to NDS. Also, using land predictions directly leads to a lot of false positives because there is a domain shift here. So in order to tackle those false positives, we learn a linear layer on top of clip embeddings and try to reduce false positives by the condition is if the clip classified class for the 2D box and the line predicted class for the 3D box are same, then we keep it, otherwise we don't keep it. So line prediction, we project it in 2D and then we compare the clip predicted class for it and the line predicted class for it. Coming to ablation study, in the first stage, as we can see, like engineered prompts per class lead to like 4.2% increase in NDS score, and then further using per class score thresholds increases map by like 0.008 and increases a few TPs on well set. In stage 2, using the heuristics of using biggest cluster for vehicle categories and nearest cluster for other categories, increases NDS score by 2.4% and map 3D by 4.2%. And finally, using land model to refine yaw and extend values, we see that so earlier the orientation error was around 1.5 radians and it drops to like 1.0 radians. So that's a drop of like 33%. But NDS wise, there's nothing much contribution to it. And further, so this is a stage 1 part, but we did it later, so it's present later in the ablation studies. Fine-tuning SAM3 on SAM classes with low recall values shoots the NDS value on well set 2.361. Yeah, so the main things that helped were having custom prompts for each class, having a heuristic to select cluster based on class category, and then fine-tuning SAM with LoRa, and using land model to reduce orientation error. So this is the leaderboard as we have already seen, and since we did not use GPT-4o or high like 72 billion parameter VLM models or VLM models with high number of parameters, we did not get very much good performance on the orientation error. Some qualitative results on the val set, like for cone category. So green box here is ground truth and red box here is the prediction in 2D and 3D. Similarly for pedestrian, for car. What did not work, we also tried other things like fine-tuning a ResNet to classify the direction of the vehicle, right, or object, like front, right, left, back, and use that as a course for step yaw estimate and then refine yaw further. So we like trained this on Kitty and Argo's data crops, but when we tried to infer this on pandaset data, we did not get very much good performance because of the domain shift, as well as there are a lot of crops with very small sizes, like less than 50 pixel, where this model failed and predicted wrong direction. We also tried using 3 billion and 7 billion parameter models instead of 72 billion parameter model to predict the course you estimate for MHT. But in our observation, that did not improve the performance on well set much. So yeah, this is where we were not able to close the orientation gap. And again, summarizing everything. So per class prompts, class synonyms help in stage 1. Having a heuristic to pick cluster, class-wise cluster in stage 2 helps. And then fine-tuning SAM3 with LoRa for low recall classes and using a 3D detector to refine yaw values helps in reducing orientation error, but not significant enough. Yeah. Thanks.
Any questions for him? Yeah, please. For the team.
Just of the problem journal.
Okay. Yeah.
I guess like you know, this task was like on bounding boxes and then turning them into cuboids. You guys have a sense of whether or not that would transfer over to the sunset task, or like learning trying to make some kind of denser representation, like maybe like a voxel grid.
I think Guanxing, do you hear the question?
No.
Okay.
Can you repeat?
Do you want to come over? Yeah. You come over to talk to the.
Yeah, I guess
Oh.
I'll just turn this off now. I guess so. Got to sort of find the boxes and then also lift that up into a cuboid. I'm wondering if you have any sense, like if you got any sense from this task whether or not that would transfer over to like maybe like would like VLMs be good at learning like SEMSEG or like some kind of denser representation of the world, like let's say like a voxel grid.
Do you hear anything?
Oh, can you repeat the question? I lost you in between.
Oh, okay. I guess we can discuss this offline. I will share your emails with the question with the gentleman, and maybe you guys can connect offline.
Sure.
Yeah.
I guess this is also a question for you as well, since like you guys did the baseline thing.
Yes, but I think a lot of the intuition also the synonyms intuition also works, no matter whether you are doing like 2D bounding box detection or like segmentation, those kind of stuff, those kind of things. So, but in terms of a specific segmentation task, we may need to run more experiments to figure out like how much it can translate. But just from the synonyms, like the descriptive terms, from my personal experiences, we do find that it works in terms of species recognition. It works in terms of 2D bounding box detection. And for segmentation, I reasonably believe that it should also works, because that is the way the foundation models are portraying it. They digest all the knowledge in the words, open word knowledge, and people use different texts to refer to different visual concepts. So it's not limited to like, is the bounding box or not. It's related to the visual concepts. Does that make sense? Yeah. All right. Yeah, thank you. All right, I think that's all for the workshop. Thank you, Guanxing, again for the presentation, and thank you all for the participants for staying us for the afternoon, and thank you all for the folks online. And we appreciate your time and the listening, and we wish you enjoy the rest of CVPR. Yeah, thank you.